We are going to have 4 talks in this session, and the first one is going to be by Arka Banerjee. Arka is going to talk about beyond Gaussian statistics for cosmology.
Okay, I'll talk about research direction that Tom Abel at Stanford and I are leading, along with a bunch of collaborators, and it's based on these papers. Given the lack of time, I won't be able to go into details, but please feel free to come and talk to me after the talk. I'll be happy to chat. So structure formation has been promised to be probes of various aspects of fundamental physics, starting with inflation, dark energy, dark matter, neutrino mass, galaxy formation physics, substructure dynamics, and so on. Okay. Now, how do we actually quantify structure is an open question. So all of these fundamental physics processes, they alter the clustering of data at late times. So whether we are talking about galaxy positions, weak lensing maps, 21 centimeter maps, the information about the cosmological parameters is in the clustering. So we need to summarize the clustering of this data into what are known as summary statistics. These summary statistics are affected by the fundamental physics, and we need to be able to predict these statistics as well, so do a comparison between our models and data. Now, more powerful summary statistics will be able to capture more information about the underlying distribution. Okay. Now, the tried and tested summary statistics in cosmology is the 2-point correlation function or the power spectrum. Now, the power spectrum or the 2-point correlation function is the complete summary statistic of a Gaussian random field. But we know that at late times, at low redshifts, the underlying matter distribution field is highly non-Gaussian. And then if you look at biased regions where the galaxies will form, these are even more non-Gaussian. So just using the 2-point correlation function means that we are actually throwing away information that exists in the data. Okay? This data already exists with current surveys already. Okay? Therefore, to make full use of information on small scales, we need to explore statistics beyond the 2-point function. There's one more thing that we need to do, I'll not go into that, which is improve our models on small scales. Anyway, how do we go beyond the 2-point correlation function? We've heard already about the bispectrum, which is roughly equal to the 3-point correlation function. That's great, that has a lot of extra information, but it is actually computationally expensive to compute, and as data sets grow larger and larger, the scaling of computing the bispectrum gets pretty prohibitive. Also, if you want to then go on and check if you've captured most of the information, you want to compute the trispectrum or the 4-point correlation function, that's even more of a nightmare. Okay? So today I'll talk about a different set of statistics that I've been developing, and I'll try to show you a few examples where we have tested it out, both on mock data as well as a few cases on real data. And in every case, we see improvements beyond the 2-point correlation function. So this is the paper where we actually propose these statistics. They're called nearest neighbor distributions. I'll quickly review what we actually measure. So suppose you want to characterize the clustering over some geometry. Let's suppose this is the square box. So first, you sample the volume densely with a set of query points. These darker points are your data. Now, for each of the query points, you try to identify where the first nearest neighbor is. Okay, so just focus on the yellow line for now. So you find the distance to the nearest neighbor. You do this for every single query point in your volume. You get a list of distances. You sort that distance. You get the empirical cumulative distribution function of these distances. Okay, you don't have to stop at the first nearest neighbor. You could do the same for the second nearest neighbor distances, and so on. 2 quick takeaways. This single measurement procedure gives me the CDF over an entire range of scales. Second, this takes about 20 seconds on a single core for a typical cosmological data set. Computing the bispectrum for this same data set takes about a few hours. Okay? But I haven't told you why this is useful. So what do these k nearest neighbor distributions actually measure? If you try to write down the generating function for these distributions, you will see that this distribution function has to be written in terms of all connected endpoint functions of the data. Okay? And then when you try to write down what the individual nearest neighbor distributions actually look like, they will depend on different combinations of all of these endpoint correlations in the data. So the more nearest neighbor distribution functions you measure, the better you can disentangle what is coming from the 2-point correlation function, what is coming from the 3-point correlation function, and so on. Okay, they are also intimately connected to the PDF approach. I will not get into that here. So in the first paper, we showed how to find autocorrelations using nearest neighbor distributions. But as has been brought up multiple times during this conference, the future lies in cross correlations. So then we expanded our method to also include cross correlations. Again, here instead of one data set, you have two data sets. Again, we are thinking about discrete data at this point. So the blue points and the green points. Now all you have to do is measure the nearest neighbor distance from every query point to the nearest green and the nearest blue. Pick the larger of the two distances. Do this for every query point, compute your CDF. I will call this the joint CDF. Again, you can try to write down the generating function for these joint CDFs. These, you will find that this has to be written in terms of all possible combinations of endpoint functions of the two data sets. Okay, so suppose you have red galaxies and blue galaxies. This generating function will include terms like red, red, blue, 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 red, blue, 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 red, red, red for the 3 points, then red, red, blue, blue, and so on. Every possible combination appears in this generating function. So if you measure this, you are sensitive to all possible cross correlations. It's also quite easy to separate out what comes from the autocorrelation and what comes from the cross correlation in this joint CDF. And if you can show that two data sets are uncorrelated in this sense, it's actually a much stronger statistical statement, because then it says the two data sets are independent, whereas if you show a lack of 2-point cross correlations, all you are showing is a lack of 2-point cross correlations, not higher order cross correlations. Okay, we showed in this paper that this is really useful for detecting cross correlations in sparse samples. Examples, suppose you have gravitational wave data and suppose you have ice cube high energy neutrino data, both really sparse data sets. The 2-point cross correlation is not able to detect the signal even when it exists, so that's the purple line. The yellow lines are what happens if you just take random samples. But if you use the KNN cross correlation, the case where there is a true cross correlation stands out truly. You can do fancy statistics with it, look at the chi-square distributions and show that if you measure the 2-point cross correlation when things are truly cross correlated, you cannot tell it apart from the null hypothesis, but with the KNNs you can clearly see a signal. Now, more towards the interests of this audience, you might also want to cross correlate discrete data with continuous maps. Okay, so Matt talked about the chime detection, I think. So that stacking is basically a 2-point cross correlation. So what we did was in this paper, we laid out the formalism for doing tracer field cross correlations. So now instead of just computing the distance to the nearest neighbor in data, you also have to consider the smoothed map on the same scale. I will not go into details, but I'm happy to talk about this in greater detail later. And then the test case that we showed in this paper was to add a really large uncorrelated noise field on top of the true galaxy matter cross correlation in a simulation. This is to mimic this really high foreground. So the foreground can be as much as 500 times larger than the signal. As you go from the lighter green to the darker green, what's happening is I'm adding more and more noise, and you can see what both the plots are plotting are basically signal to noise. On the left is with the 2-point cross correlation, on the right is with the nearest neighbor distributions. As we add more noise, the significance of the signal to noise actually goes down. It goes down pretty drastically in the 2-point cross correlation. So if you add 500 times the amount of noise as compared to the signal, you get a very low significance detection of the 2-point cross correlation. But for the same amount of noise, if you compute the KNN cross correlations, so these gray bands are the error bars, you get a really significant detection. Okay? So what I showed were papers where we actually laid out the formalism to do these nearest neighbor measurements, but we've also actually applied this to data already. Simple application. This is detecting the spatial clustering of the 1,000 richest SDSS red mapper clusters. So again, this is an extremely sparse data set. So this is 1,000 data points over the entire SDSS volume. This should be drowning in short noise. If you were trying to measure the 2-point correlation function, you were trying to measure the bispectrum. Okay, I will not do that. It will be even further drowning in noise. Okay, this includes all survey systematics, coverage, survey volume effects, masks, everything. Again, what we did was given the red mapper randoms. So SDSS gives us the red mapper randoms. This is the chi-square distribution of the clustering of the randoms. We had 1,000 realizations of the randoms. This is the measurement of the actual 2-point correlation function, autocorrelation function. So you see that you might be able to detect the 2-point correlation function in this data set. But if you try doing the same with the nearest neighbor distributions, you get a whopping signal here. Okay. Again, to reiterate, this was just 1,000 clusters. We were also able to show, I didn't go into this, but the KNNs can actually be used as a test of Gaussianity. We showed that this data set is not consistent with being drawn from an underlying Gaussian distribution. Of course, everyone knows that, but we could prove it within the data. We are also close to having our first application to continuous data. So this is using the dark energy survey weak lensing maps. So we use the autocorrelations and the cross correlations between the wide tomographic lensing maps. So there are 4 tomographic bins between redshift of 0 and 1. So we use the autocorrelations and the cross correlations between them. And what we are finding is that this nearest neighbor method outperforms not just the 2-point correlation function, but it also outperforms the second plus third moment calculations. And it's actually very close to having information from the second, third, fourth, and fifth moments in the data. Okay. So this is work in preparation. Hopefully, it should be out in a couple of months. While we've been focusing on first detecting these things in the data, you also want, if you really want to do cosmology, you also want to be able to model these as a function of cosmology and parameters that control galaxy formation. What we were able to show is that the recipes that you need to model these already exist. People have developed these bias formalisms to take care of the 2-point cross correlations. We use pretty much the same procedure to show that you can you can model the KNN statistics as well as a function of both cosmology and bias. So focus on the solid line in the regions where there is no gray shaded bars. On those scales, we get unbiased predictions for the nearest neighbor distributions. So this is the residual between the predictions and the actual measurements on simulations. Now that we have a model, we can actually try to predict how much better we do in terms of recovering cosmological parameters compared to the 2-point function. For things like sigma 8, with exactly the same data set, we do a factor of 3 better in terms of recovering sigma 8. And this is actually driven by much better constraints on the bias parameters coming from than from the 2-point correlation function. Okay, so a better measurement of the bias actually drives this improvement in sigma 8. Okay, as my time is almost over, this is my summary slide. So, understanding structure formation in the universe can help answer some of the most fundamental questions in physics. But to really do that with the existing and upcoming data sets, we have to think beyond the 2-point correlation functions. The nearest neighbor distributions is one way to do it, but I think we have shown in a number of different test cases that this is a cheap and interpretable path to higher order statistics. In every test case we've thrown at it, it shows much greater statistical constraining power than the 2-point correlation function. And actually, even compared to the bispectrum, I didn't show that plot here. There are many potential applications in cosmology and also things like gravitational wave clustering and beyond. There's nothing that keeps this in 2 or 3 dimensions. You can actually apply this to, say, time series data in 1 dimension and look for clustering there. There are also some fun connections with geometrical and topological measures of clustering, such as Minkowski functionals and Betti numbers. So if that's where your interest lies, you can explore that as well. So in the interest of time, I had to rush through this a little bit, but I'm happy to take your questions and chat about this later as well. Thank you. The scale cuts. So once you have measured the cumulative distribution functions, you can cut at the scale that you want. And you can show that the analysis proceeds exactly the same way as the two-point correlation function.
Thanks, this is great. This is actually related to some techniques in two-dimensional quantum gravity where they use causal dynamical triangulation. You mentioned something about correlating ice cube neutrinos with structure.
Yes.
Do you have that plot here?
Not using the nearest neighbor distributions. We have a paper in 2020 with Ke Fang, where we actually did this with just the two-point correlation function. So we did a full cosmological cross correlation of ice cube, high energy ice cube neutrinos with the unwise galaxies.
I see.
We at that point, none of us were part of ice cube, so we only had access to the 3-year data, and it fell just below the detection threshold. But now Ke is actually part of ice cube, and she is doing the full calculation with the 10-year data. Let's see where we get with that. But then the next we are using this.
Okay.
Yeah.
Look forward to that.
This is very nice. So I was just wondering, and maybe you touched upon it a little bit, but not in great detail, how to expand this to continuous fields, right? For example, in 21 centimeter cosmology, we're measuring continuous fields. Of course, often not in correlation functions, but in power spectra. But they're sort of equivalent. So it would be very interesting to see if it's applicable there.
Yeah. So at least for the cross correlation, we have the paper is already out on how to do this. I can talk in detail about exactly what you need to measure. And this paper that's under prep, where we apply to the lensing maps, we are applying this to a fully continuous data. In the sense, it is gridded, but it's
So you're just treating pixels as points in that case. Okay, thanks.
Hi, Arka. When you are applying it to cosmological simulations, you have all the information, I can understand, like mass, position, and all this stuff. But when you are applying it to SDSS data and all, there are a lot of galaxies missing because of the sensitivity, and we don't have the mass information. So how reliable your cosmological parameters will be?
So the mass actually never enters here in this particular calculation. Things like, are you worried about fiber collisions? Are you worried about fiber collisions, or are you worried about, say, the survey geometry? So SDSS does give you, what they think are complete samples in a certain sense, but you might still be worried about fiber collisions. So there's a paper late last year, led by Sandy Yuan at Stanford, which actually shows that even in the presence of that looked at DESI and not SDSS particularly, it showed that with DESI, there is a way to recover these statistics in an unbiased manner, even in the presence of fiber collisions. Survey geometry, masks, we have already taken into account in this paper. All you need to do is take your the query points, instead of distributing it over a box like you would do it in a simulation, you just use the mask to do it, the survey mask. Okay. It's similar to how in the two-point correlation function, if you use the Landis-Allee estimator, there's the random term, there are the randoms which take care of the survey geometry. Very similar to that.
But RSD effect will be always...
Yeah. So that's there in the two-point correlation function as well. How do you model that there? Right. Same thing. You'll have to build it either into your forward model, or you somehow have to remove that. All statistics will be affected by it, not just these.
Right. Let's thank the speaker. And so next talk is by Rajeev, and he's going to talk about primordial black holes from inflation.
Okay. So good morning, everyone, and let me start by thanking the organizers for this kind invitation. So I'll be talking about primordial black holes from inflation and their observational imprints. So I'll go further back in time compared to what Arka was talking about. And this talk is based on a bunch of papers which form part of the thesis of my first PhD student, Niranjan, who probably is not here in the audience. He was here the last few days, and he also put up a poster outside. So if you're looking at more details, please look at the poster as well. And if we consider inflation to be the correct description of the very early universe, we also know that inflation must last for 60 odd epochs to solve the horizon problem. Okay. We also know, thanks to the precise CMB observations, mainly from Planck, the spectrum of primordial fluctuations on the very large scales, so-called the CMB scales, is well constrained. It's a nearly scale invariant power spectrum with a very precisely inferred amplitude and a tilt. Okay, that is something we know from CMB observations. And this just corresponds to about 8 to 10 e-folds of inflation. Okay, there still remains about 50 e-folds of inflation that we do not have much idea about. It was discussed on the very first day in a couple of talks that CMB distortions, which sort of correspond to about 15 to 20 e-folds of inflation after the CMB scales, they have an enormous potential to constrain the physics which happens in the next 10 to 15 e-folds of inflation. Despite that, we still are left with still around 30 e-folds of inflation, which there is no way to constrain. That's where the primordial black holes, which I will discuss what do I mean by them and how can they be produced in the very early universe, come as a rescue or as a novel avenue to constrain the dynamics on the small scales during inflation. So the plan of the talk is as follows. I'll very briefly discuss why do we need to understand and worry about primordial black holes in the first place. What do they mean? How can they be generated in a simple framework of single field inflation? And I'll particularly focus on one class of models called the inflection point models. I'll then talk about how to compute the scalar power spectrum in these models and how to compute the so-called the PBH mass fraction. I won't go into the details of all these calculations. And then in the second half of the talk, I'll talk about some very interesting observational imprints of primordial black holes. The first part will correspond to so-called the induced secondary gravitational waves, and I'll show that these secondary gravitational waves will have a very interesting peaked spectrum which can be detected with the bunch of upcoming gravitational wave observatories. And in the second part of my talk, I'll talk about very interesting imprints from the Hawking evaporation of black holes and whether they can also contribute to the relativistic degrees of freedom that we can constrain from CMB, as well as the stable heavy particles which are emitted from these black holes could also constitute the dark matter in the universe. And then I will summarize. So we know that dark matter does exist in the universe, and however, we do not know what is the candidate, the true candidate of this dark matter component. Among these many possibilities which have been listed, which may not be an exhaustive list, in addition to the fundamental particle-like candidate for dark matter, and in addition to these modifications of gravity, there are also these class of candidates which fall under the so-called the macroscopic candidates, which have also been proposed as possible candidates of the cold dark matter. And primordial black holes happen to be one of those macroscopic objects which have recently gained a lot of interest thanks to the LIGO observations of subbinary black hole mergers. So why do we need to consider primordial black holes? They are very interesting and promising candidate for the cold dark matter in the universe. Inflation, by its own virtue, with the non-trivial dynamics on the very small scales, can generate primordial black holes, and abundantly, so that in some mass range, these PBH can be the entire dark matter. They are non-baryonic, non-relativistic, and nearly collisionless, which makes them a very unique candidate for the cold dark matter. There's apparently no new physics required. Whatever physics that drives inflation can also simultaneously produce primordial black holes on the very small scales. And as I said, that there is some hint about some candidates, some binary black hole candidates from LIGO detection, and the seeds of those candidates could possibly arise from primordial black holes. So this plot illustrates various constraints that we do have on the parameter space of PBH mass fraction, the fraction of energy density of PBH in terms of dark matter as a function of mass normalized by the solar mass. And you find that in addition to all these constraints which arise from femtolensing, microlensing, and other things, there still remains these two interesting mass windows where primordial black holes can be the entire dark matter. And there has been a lot of interest in exploring models which could contribute to the dark matter entirely in this particular mass range. So as I mentioned that there are a bunch of candidates in the LIGO detection of binary black hole mergers, and some of these candidates could also indicate that they might be primordial in origin, and people have also discussed a lot about whether LIGO could have possibly detected dark matter, but I won't go too much into the details of this discussion. one interesting aspect of some of these candidates from LIGO is that some of these observed sources are consistent with no spin. You would otherwise naively think that any astrophysical black hole should necessarily have a spin because of the accretion and all these phenomena. This expression indicates the lifetime of the black holes, in the sense that if black holes after their production are supposed to Hawkingly evaporate, then there is a mass range, there is a lower limit on the mass range on the PBH mass. They would only survive the age of the universe. Any black hole with mass less than that would completely evaporate by the end of, by today, and henceforth will not constitute to the dark matter. And people have also discussed that if in future we do detect sub-Chandrasekhar mass black hole, it must necessarily be a PBH. So this slide sort of gives you a crash course on the PBH formation. So this is what we understand, that the large scales, when they leave the horizon, they re-enter during the radiation-dominated epoch, and these large scales correspond to the CMB scales. And we also know that the amplitude of these spectrum and the tilt is well constrained by CMB observations. However, as I mentioned, that the small scale dynamics, which leave the horizon much later but re-enter early, is not so constrained. And if you have large overdensities on these scales, they could potentially form primordial black holes when these modes with large overdensities re-enter the horizon during the radiation-dominated epoch. This is what we are interested in. We are interested in understanding this non-trivial inflationary dynamics on small scales and how a particular model can produce PBH. So once again, this part of the parameter space, what I'm plotting is the amplitude of the density fluctuations as a function of the co-moving wave number. This part of the parameter space is well constrained. We know that this is 10 power minus 4 minus 5, and this is the part that we would like to constrain using PBH. Okay, and so there's a lot of, there's an order of magnitude difference, because as we would see later, you would need the power spectrum to be of order around 10 power minus 2 to have a large enough abundance of primordial black holes so that they can constitute a larger fraction of the dark matter. So I won't go into details of many mechanisms that have been proposed. I'll just focus on the single field inflationary mechanism with this simple inflection point potential, and the idea is as follows: that if you have a potential which also contains a point of inflection, the large field plateau of such a potential would correspond to the CMB scale, and henceforth you will have an initial slow roll phase, thereby giving rise to a nearly scale marine spectrum with all the constraints being satisfied. As the field rolls down towards the plateau of the potential, you would eventually go into something called the ultra slow roll phase. And it has been shown that such an ultra slow roll phase, because the dynamics of the system, gives rise to an exponential enhancement of the power spectrum, and with the global minima in the potential, the field eventually rolls down to the true minima, thereby ending inflation. So we looked at a particular class of potentials allowing a point of inflection, and we find that in this particular example, both at large and small field values, the potential still behaves like a quadratic potential. You would expect that because of this behavior on the large scales corresponding to the large field values, the tensor to scalar ratio will turn out to be large, and henceforth these models would be immediately ruled out. However, we found that because of a subleading contribution arising from these other terms in the potential, the tensor to scalar ratio still is just around the constraints that we have. So I won't go into the details of all the understanding of slower and ultra slower dynamics, but if you just do it carefully, you find that the power spectrum, which is nearly scale invariant on the very large scales, has this exponential enhancement due to this ultra slow roll evolution on these smaller scales. And by choosing this so-called the point of inflection in the potential, you can have this enhancement on a variety of scales in the power spectrum, which would correspond to an independent mass range when you compute the PBH mass fraction. So which is what we compute with that spectrum, and we find that you can have these fractions in these different mass windows as compared to the dark matter energy density. And you find that in these mass windows, because there are already constraints which disallow this part of the parameter space, you can only have a fraction of dark matter in terms of PBH. However, in these two interesting ranges, PBH produced in these models can be the entirety of dark matter. So there was one interesting aspect that we found in these class of models. As you can see, you just need to see carefully that if you want to produce PBH corresponding to these scales, the spectrum on these large scales also gets affected. This is what we noticed, that it might not be so easy to form PBH at all mass scales or all mass regimes in this particular model if you want to stay consistent with the CMB constraints on the very large scales. So this plot essentially shows the NSR contours as a function of the different masses, and keeping in mind that this the spectrum is nearly monochromatic. We find that only very small mass PBH are consistent with the NSR constraints on the very large scales. We further looked at the effects of reheating, and we found that there is a slight shift in the PBH mass fraction and the spectrum as well. I won't go into the details. So I will now talk about the stochastic gravitational wave background that are produced from any scenario of PBH formation during inflation. And this essentially is a second order effect that you can think of in the gravity wave equation, because at the second order in the scalar fluctuations, this source term arises, which you would have neglected in the first place, because the amplitude of these scalar fluctuations remains small in an otherwise low roll single field inflation. However, in all these scenarios of PBH formation, because this amplitude is now much larger, and therefore you need to worry about the source term on the smaller scales, which in turn lead to an induced spectrum of gravity waves in addition to your primordial or primary contribution arising from the inflationary tensor fluctuations. So before I go into discussing the spectrum, let me just point out this interesting relation between the mass of the PBH which are produced in a particular model of inflation to the wave number at which the power spectrum shows an enhancement to the frequency of the induced gravitational wave spectrum that you are going to produce. Okay, and you find that the PBH which are produced in this asteroid, so-called the asteroid mass range, will almost lead to a peaked GW spectrum which would fall right in the sensitivity band of LISA observatory. So this is what we find for these different spectra that I showed earlier, that you get these different induced gravity wave spectrum with this very nice peaked structure for this different inflection point of the model. And we found that our numerical results are also consistent with some of these universal IR scaling that have been worked out in some of these papers. So the numerical spectrum matches absolutely well with the analytical or approximate results that have been obtained to understand these spectra. And once again, we looked at the effects of reheating and found that there could be a secondary enhancement of the GW spectrum on further small scales or further higher frequencies if you have a specific matter-dominated regime after the end of inflation. So let me very quickly talk about yet another interesting imprints arising from the evaporation of PBH. Okay, so let's be agnostic for a moment and don't care about what produces the PBH in the first place. Let's just consider a distribution of PBH which we take to be ultralight, in the sense that we assume that all these PBH would completely evaporate by BBN, and therefore they will not contribute to the dark matter at all. However, because of their evaporation during this epoch of their formation to the BBN, they are still going to induce a bunch of observational imprint. That's something we looked at. So this is what you have in mind, that you have an epoch at which these PBHs, which are ultralight otherwise, could dominate the universe. So we call this an early matter-dominated epoch because PBH behaves as matter with W equal to 0. And we find that the first imprint is that in addition to the first peak that I talked about, there's going to be a additional resonant peak in the GW spectrum itself. And this arises from the fact that this distribution of PBH is also going to give rise to so-called the isocurvature fluctuations, which could be converted into an adiabatic component. And these adiabatic component, using the same formalism that I discussed, the second order scalars, is going to give rise to another contribution. So which is what we found, although the secondary peak turns out to be at much larger frequency, and the two different plots here correspond to the non-spinning black holes, which are characterized by this parameter A star equal to 0, and also the almost maximally spinning black holes with A star equal to 0.99. The spin does not play much of a role in at least the shape and the amplitude of the GW spectrum. We also find that because of their evaporation, they are also going to contribute to the extra relativistic degrees of freedom. That is also well constrained from CMB observations, as we know. So what we find is that, again, for the different cases of this spin parameter, and considering the evaporation of these different kinds of particles with different spin, s equal to 0, 1, half, and 2, we find that the contribution of these particles to the delta n effective, the relativistic degrees of freedom that you can calculate, is very different. In particular, let me draw your attention to the fact that the maximally spinning black holes are going to have a maximal contribution to the largest, to the particle with highest spin. This is what we find, that if you look at the graviton case, for the A star equal to 0, the contribution remains really small. But for a maximally spinning case with A star equal to 0.99, the contribution is really shot up. Okay, and as a result, you find that in this window, with these upcoming experiments, you can potentially detect or constrain these contributions arising from the PBH evaporation. All right, and then we looked at some further sensitivities of the future upcoming gravity wave observatories for a given SNR, and we found that some of these scenarios that we have considered can actually be constrained. So this part, which is white, actually is the allowed parameter space that can potentially be constrained. So let me conclude. So as I discussed, PBH are novel candidates for the cold dark matter, and more importantly, they are a very interesting probe for the small scale dynamics during inflation. Inflation can produce abundant number density of PBH, and these simple models that I have discussed are very useful. The induced gravity waves that I talked about, these signatures can be probed by LISA, DeSigo, or BBO, any of these future upcoming observatories, because the spectrum is peaked and very wide. And one interesting aspect is that, which one can call as a testable prediction, that if we do not observe these characteristic peaked gravitational waves, you can possibly rule out PBH's dark matter. Interestingly, PBH, even if they do not contribute significantly to the dark matter, they are still going to contribute to the stochastic gravitational waves. And finally, as I discussed, that the PBH evaporation for these ultralight PBH masses can also lead to dark radiation and dark matter, and they are constrained from future observations. Let me just mention one more comment, is that this mechanism of dark matter protection through the stable heavy particles from the evaporation actually is a non-thermal way of producing dark matter, contrary to the thermal freeze-out mechanisms that we are aware of in the early universe. So this would also be an interesting test to probe these non-thermal mechanisms of dark matter production. I'll stop here. Thank you.
Thanks, very interesting. I have a concern about this idea that you tune the amplitude of inflationary perturbations by letting epsilon or phi dot or whatever. If you could show that formula again, then maybe it'll be clear to people. So you have h square over epsilon.
Right.
Now, obviously, if epsilon goes there, epsilon goes to 0, this thing blows up.
Yeah.
But this is a perturbative formula. It only works when the perturbations generated are small.
Mm-hmm.
Otherwise, you have to take into account the back reaction of the fluctuations on the evolution of the inflaton. And you are, in fact, tuning it so that you have a factor of 10 to the 10 jump in that next plot.
No, just 10 power 7.
Okay,
So,
10 to 7, fine, fair enough.
The spectrum here it still remains 10 power minus 2.
Yes,
so it is
still perturbative, I agree. But that you set by hand.
That is something you would like to have.
Yes.
Keeping in mind that that amplitude is going to give you abundant.
I understand. You want to keep within the observational bounds.
Yes.
But what I'm saying is that epsilon, the limit of epsilon going to 0 does not exist for that formula. Epsilon of 0 is de Sitter space.
Right.
You cannot go from inflation back to pure de Sitter space, which has no arrow of time. Epsilon gives you the arrow of time.
So let me just clarify. First of all, none of these formulas, like h square over epsilon, is not really valid for epsilon strictly going to 0 limit.
Exactly, that's my point. So you are setting it to be controlling.
You are just taking epsilon going to a smaller value because you want to produce this enhancement, but you are never ever going to take epsilon going to 0.
But there is no back reaction effects at this level.
No, because this still remains perturbative.
Okay. But that you set by hand by choosing the
Yes.
slope to be appropriate to
Yeah.
obey all the observational
Yeah, so in terms of these inflection point values,
I understand.
we sort of, there's a fine tuning involved, I agree.
Yeah. Okay, I understand. Thank you.
So my question in the context that PBHs are being proposed as candidates for producing supermassive black hole seeds early enough. Could you describe some sort of mechanism where that could possibly happen? They would have to coalesce despite inflation to produce seeds.
If I understand correctly, there are two thoughts. First is that we all know very well that you cannot produce supermassive black holes within lambda CDM, right? Within lambda CDM, you cannot really produce supermassive black hole. That is my understanding.
Right. No, but seeds, which
so
would
basically, if you have produced PBH in the first place in the very early universe, those PBH, even if they are not contributing to the dark matter, but if you have produced them in a larger mass range, they could survive and still behave as a seed to, for the later universe, in the sense that the accretion and everything could take place, and those could eventually become the population of supermassive black holes.
Right. My question was, can they coalesce in this scenario?
Yes.
Can they coalesce fast enough to produce, say, 10,000 solar mass black hole seeds by 300 million
Whether
years?
they can coalesce faster is, I'm not sure, but people have talked about the merger of PBHs in a binary system, and of course, over time, they will eventually coalesce.
Right. Let's thank the speaker again. And next talk is by Subinoy Das, and Subinoy is going to talk about new physics to solve Hubble tension.
Okay, thanks organizer for inviting me for this talk. So I'll be talking about Hubble tension, and mainly from theoretical side, what is the solution people are thinking about. So before I go to the talk, I'll just give the conclusion in the beginning that Hubble tension is a serious tension. People are thinking there is no solution yet. So if somebody claims that there is a solution, it is overstated. And if somebody says that Hubble tension is not a tension, that is also, I think, little immature conclusion. So this work, which I'll be talking about here, two paper, is done with my final year PhD student and with Tanmay Karwal, who was Mark Kaminkowski's student, now with postdoc at KICP, and Vivian Pole is a faculty at Mott Bartlett. So Hubble, the expansion of the universe has given trouble from the beginning. So Einstein was troubled. And here is a picture, rare picture, Hubble and Einstein together. Definitely Hubble is not proving that, see, look at the universe, it is expanding. But we know that Einstein was troubled. So now what is the Hubble tension? I'll briefly tell. So there are two ways to determine the value of Hubble parameter. One is from Planck, another is from late time direct observation. But here is a disclaimer that CMB does not measure H naught directly. But if you have a model of the universe, then you can infer the value of H naught. So here, like when Planck says that they have measured H naught to a low value of 67, and where the direct experiment like Holy Cow shoes or other, there are many, when they measure, that is a direct measurement. So if there is a discrepancy of 5 sigma, then there are two ways. Either like this part is wrong, or when we say that the CMB measurement is wrong, that is another option, but that is not true. Also the late time people also say they have not found any systematic yet. So then only one option remaining, that this assumption which goes with the Planck, that whether it's a lambda CDM or other universe, that's where people are playing about, because that's where you can change the H naught measure from CMB. So that's why the theory become important, because when you want to solve this mismatch. So here I was visiting Johns Hopkins. So this is an email from Adam Rees, who discovered acceleration of the universe. So he thinks that this discrepancy or this problem is even stronger than when he was looking into the data of the supernova for acceleration of the universe. And I was discussing with him, he said, like, if lambda CDM passes this H naught trouble, then lambda CDM is really going to be the model of the universe. So it's far away that we can say that H naught trouble is, lambda CDM cannot solve the H naught trouble yet. So here is as I mentioned, there are three ways to solve this problem. One is problem with local measurements, direct measurement, but most probably it is not.
or problems with CMB measurement, which is most probably not, or both. So only one thing remaining here as a theoretical physicist is good news, that maybe new physics. We can do something. So here is how CMB measures H naught. So CMB does not measure H naught, as I said, but it measures this theta angular, and then that theta is RS, the sound horizon, divided by the dA, angular diameter distance. So this RS by dA is fixed by CMB measurement. So now, if you, this dA, if you have a cosmology, and you will see that you will get a term 1 by H naught kind of term. So basically H naught comes from here. So that's why if you measure theta S, then RS by dA gives you an H naught. So now, if you have to solve this discrepancy, there are two approaches people has taken. That otherwise, either you change the dA, that how, what is the geometry of the universe, that the nothing wrong with the photon release, or the CMB physics is the same, but how the photon is traveling from CMB last scattering surface to today, that changes dA. So that changes your H naught, because you have a, if you have a different dark energy model or late universe model, or you change RS. But it happens to be all the late universe solution does not work. I will not go into the detail. It is because of the BAO data. We can discuss later in detail. So nowadays people are thinking about, if there is a theoretical solution, it has to come from the early universe, like before CMB physics, and there is something beyond lambda CDM going on there. Something new physics has to be there to solve this H naught tension. So here is a cookbook. If you do little analytical calculation, you get H naught with H recombination, and here you see that above is RS, below is the RS from 0 to T recombination, and the T recombination to T naught here is the geometry, because C dt and the stuff in the universe, which contributes to the geometry. And whereas here you will see the CS enter, which is the sound horizon, the photon speed. So this is the integral from 0 to the CMB time, and there is above is the integral from CMB to present. That basically late universe, that is basically early universe modification, and people are now trying to change this. But here, as I said, you have to change that. Here it's very hard to change the CS, because that's fixed by the particle physics. So only thing remaining here is you change the rho T, the amount of energy density, amount of, because in a lambda CDM model we know that photon and the 3 neutrinos were dominating and dark matter that time. But if you have to put something else to make the decrease in this quantity, so that H naught will increase from CMB when you feed the data, means when you measure the theta S and want to find out what is H naught, and then you have to increase rho T before CMB. That means you have to put some extra component in the universe, and that's not so easy. And how to do that? Before I go, so some people who believe that dark energy or late time universe is not the solution to H naught, they think that H naught discrepancy is nothing but a sound horizon discrepancy. So sound horizon from CMB is around 135 or 40 megaparsec, and from late time universe it comes out to be 150. So you have to reduce the sound horizon by 10 megaparsec to solve the H naught tension. But if you plot the sound horizon for a normal cosmology as a function of Z, it becomes 10 at redshift 10 to the power 4, or like say 10,000, little bit before that. So if you change physics here, the sound horizon value even does not reach 10. So you cannot change the sound horizon value more than 10, which we need to solve the discrepancy. So basically your new physics has to come below redshift, say 10,000. So new physics just before 10 CMB, that is like electron volt scale, is very hard. So that's why only one thing comes there, new physics you can play, that is neutrino. So that's why you will see most of the particle physics solution for Hubble tension is something to do with the neutrino. Either make the neutrino interactive, or you put an extra generation of neutrino, or I have also worked on this one such model, or neutrino assisted dark energy. So that's why, because it's very hard to put a new physics just before CMB. So the classical solution, people thought, is okay, let's have a little bit extra radiation, maybe coming from a fractional degree of neutrino, fractionally thermalized, because you cannot have a full thermalized degree of freedom ruled out by Planck. But this does not work. This is when Rees published this paper of Hubble tension, they tried to solve Hubble tension by adding a little bit of extra radiation, because that will increase the expansion rate, rho T, which I was talking about before CMB. But what happens, to be consistent with Planck data, it can go just touch the Rees measurement of Schu's measurement. So you can see it cannot even come within 1 sigma of Hubble parameter. It can 74, it cannot even go to 74, 72. So that's why this does not work, just increasing a little bit extra radiation. So then, this is the group, Minkowski, that is one of the most famous solutions. It's called early dark energy. It has more than almost 1,000 citations in 2-3 years. Here they say like, okay, if putting radiation does not work, let's see if we have a multiple episode of dark energy in the universe. Now we know that dark energy is there and we don't know what it is. Maybe there is another episode of dark energy, and they showed, I'll not go into the detail, if it has to solve Hubble tension, if it has to change the rho T, which I was talking, in the exact way to match the H naught, then the dark energy has to appear around 10 to the power 4, that region, as I was saying, new physics. So 3500 is the peak, or redshift 3600, and it has to decay also even fast. So it's like a peak and decay of dark energy, and which is extremely fine-tuned, because nobody knows how dark energy, new dark energy can come here, and then it has to fall apart, and then this little bit with redshift window, it give a kick to the expansion, rho T, and that solves the Hubble tension. But there are problems with it that I'll tell that detail. First of all, this is fine-tuned, extremely fine-tuned. Nobody knows why dark energy appear, another dark energy appear, and the next one is it makes the sigma 8 tension worse. There is another tension of sigma 8, that the Planck value of sigma 8 is a little bit higher than the weak lensing value, like from the Kids experiment, around 2 sigma or 3 sigma tension. So that's what this is a reality check. Normal neutrino does not work, and if you do a localized injection, then there is a coincidence problem in the electron volt scale and need very complex physics. And this is what I was telling, that what is the problem, because when you make the rho T go high, a little bit up before the CMB, it gives an early ISW effect, because your universe is expanding a little faster and the gravitational potential is changing faster, and because of that, you have to compensate that early ISW effect to make the CMB spectrum right. You have to increase the matter density a little bit more, and because of that, your sigma 8 increases. So it makes the sigma 8 tension worse. So we tried with Tanvi, Mark Kaminkowski's student, and myself, that what about you don't put extra radiation, but maybe the dark matter, because there are many models, the dark matter can decay into, like, say, radiation, like photon-like particle or dark photon, and that produces that extra kick. So initially we got a very promising result. We published also, and here we see that the solution, this is one shade is for the shoes, another is for the sigma 8. So you see that the 1 sigma range of shoes H naught value is, we are reaching it, with the red one is for our model and blue is for lambda CDM. And we are reducing S8, and because our dark matter is actually decaying, that's why matter is decaying, so you are decreasing the clustering. So we thought it's a great solution, because like unless early dark energy doesn't do the early dark energy, it goes like this way. So if you want to solve the Hubble tension, your S8 become worse. But when this was done with Planck 2015, we are doing this paper at 2017 or but with Planck 2018 result and taking the dark matter decay from ISW effect, late ISW effect, it actually, the solution does not go all the way to that. So we did not write another paper to say that it does not work, but it does not work. So then we tried with a neutrino physics that to solve that coincidence problem. Here many people are trying that neutrino become non-relativistic during CMB, and when it become non-relativistic, its rho minus 3p, the energy momentum tensor, become non-zero. Before rho minus 3p is 0. Generally all particle physics models, the energy momentum tensor coupled with the fluid of dark energy. So because of that property, the dark energy will only kick in or become active before CMB, because when neutrino become non-relativistic. So So these models are still from particle physics are well studied, and if you will see that all neutrino assisted early dark energy. But one thing that none of them solve the sigma intention. So now, so this is the paper. Now this is a recent work which will come out next week with Vivian Poulet and my PhD student. So we say that, okay, is it really necessary that a early dark energy has to be -1, W equals to minus? Can it be a dynamical dark energy like quintessence? So we took a model independent approach and we found out that indeed there is a 1 sigma detection that it is equation of state is not -1. In fact, if it is -0.7, it does better, give better solution than the normal cosmological constant type early dark energy. But more than that, we have asked another question, whether we really need a dark energy. We know dark radiation does not work because N effective does not work. But what about any fluid between N effective, between 1/3 and -1 or 1/3 and 0, and we run a simulation in the model independent and we show that it actually works better. So this paper is coming next week. So we don't need an early dark energy to solve H0 tension. It can be any fluid, but there will be an equation of state bound on that. So maybe we have to let go the solution that there has to be another early dark energy. Any fluid, but equation of state is between radiation and some value, which you will see next week. So my conclusion that maybe this Hubble tension is telling us that the cosmological model of which we believe lambda CDM is just an approximation to a larger reality, and whole game of solving Hubble tension is energy injection in a very narrow window, and it has to decay, and then it has to decay faster. I didn't tell it, so that's why there is a sharp decay. You cannot just keep that component. It has to decay faster than 1/a⁴, and even a non-dark energy fluid can do the job. That will come out next week. So thank you. Yeah.
Questions?
Yeah.
So there's a Hubble tension,
Yeah.
there's a sigmoid tension,
Yeah.
and there's also the consistency with the BAOs.
Yeah.
So are there scenarios which sort of
So
solve
that's
all of
why
them?
if you just put Hubble tension and the sigmoid tension and Planck data, even the late energy solution works nicely. But if you put BAO,
But they are not consistent with BAO.
not consistent. That's the thing. But if early dark energy is okay, it does not. But the late dark energy model completely ruled out when you put BAO.
So there are
They are consistent. The early dark energy is
models which are
consistent, but the solution, the sigma goes little bit off, but
Okay.
it's still okay.
okay, at least easing out the
Yeah,
tension.
yeah, definitely.
Two things. First, one comment. So it's, I think we should be a little more precise than breaking up the measurements into early and late, because if you look at the SHOES supernovae, they go out to redshift 1.
But
On-
the
on the
data
other-
here is 0.15. All the Cepheids.
No, that's the lowest rung of the distance ladder.
Yeah.
But if you look at the supernovae,
Ah,
they go
that's
out to redshift 1.
One, yeah,
On the other hand, the BAO measurements are often at lower redshifts.
yeah.
So calling them early and late measurements is not quite correct.
Yeah, I didn't call BAO as the late measurement. I said the late solution.
No,
from
no,
the,
in your first slide,
Oh,
taken
first
from
slide.
Anwar.
Oh, okay. Yeah,
Yeah.
got it. Yeah.
And the second one is, if you just go to the previous one, are you combining SHOES here?
Yeah, this age not prior from the SHOE.
But if you have two data sets and you see a tension, is it okay to combine them in this form? Shouldn't you rather open up this new
So there has been controversy on this because this is
Yeah.
the approach people took.
I know,
But
I
then
know.
the whole chi-square analysis and all these things comes. But they are actually, these two data does not match.
Shouldn't
with
you
the-
just open up Planck to this new W? See if Planck prefers a value which is
Yeah, good point. But here, if you take Planck and ACT, then you go to try to solve the thing because you don't need the H0 because there is a paper by Vivian.
that is actually that's interesting because it says Planck itself prefers some different H0 if you open
But
up
with
that.
the Planck alone, without H0 prior, you do not go to a higher. But it does not prefer.
But it's dangerous to assume that as a prior if the two data sets are conflicting.
Yeah, just wanted to, you missed my talk on the first day. So you can solve the Hubble tension without changing any expansion history also.
By neutrino,
Yeah.
okay.
So we don't change any expansion history.
But
There's
you
no
change
early
the
dark
neutrino
energy, no
property.
late dark energy, everything is as lambda CDM. You just introduce the phase shift because there is a phase shift also.
So interacting neutrino.
So the formula that you show, the theta
Yeah.
is not RS over D. There is another phase shift factor there
Yeah.
that you miss.
Yes.
thank the speaker. Next talk is by Ashok Singal, and he is going to tell us about dipole asymmetry seen in large radio surveys.
Hello, I'll take you down the memory lane. This is 47 years back in 1976 January, so exactly 47 years back. Here you can see the building where we generally have the tea. So then this main building was there, but I think library and where we have our lunch, that was not there, and some other buildings came up. And some of the people you can perhaps recognize. This is Rad, and this is Srini, and this is of course me. RRI in his 20s, I was also in 20s. In fact, most of people were, except the teachers. And this Sushma Malik, and Ramana Murthy, and V.R. Venugopal, Kumar, Saikya, and Ashok Pati, like that. Some of the people you may know. Some, and Chanda is there, yes? Yeah, Chanda is there. I don't know where all the people are now, by any case, so I thought it may be good time to just, pardon? 76, yeah. Any case, so I hope, yeah. So this is my talk, so I request the chairman to add 2 minutes to my time to also show the photo. Any case, so this is the title of my talk, and if sounds Greek to you, you can have a look at the photo, that who is who. Any case. So I'll be talking on something which doesn't seem to fit with the cosmological principle. So just to define cosmological principle, or rather what cosmological principle says, that says to a co-moving observer, the universe should appear homogeneous and isotropic. Or all directions should appear, because homogeneity we cannot easily check, we cannot go there, but isotropicity we can check. However, if the observer has a peculiar motion, like we are part of solar system and solar system is moving, then that may introduce some of the properties may end up having some dipole anisotropy due to that. Now, cosmic microwave background CMB shows a dipole anisotropy, which has been interpreted as motion of the solar system, which velocity 370 km per second in certain directions. Now, this was of course till about 10-12 years back, but then AGNs also can be used, which are at redshift of 1 or distant. Those also can be used to work out the, by looking at dipole anisotropy in those, you can also work out what could be the motion, peculiar motion of the observer, that is solar system, we are part of that. And then NVSS was the only catalog available about 12 years back, which had large sky coverage and a lot of sources, about 1.8 million. Although we don't use all 1.8 million in our analysis, because we restrict to certain flux range. Any case, so it showed an asymmetry, dipole asymmetry, which gave a velocity which was 4 times the CMB value. So that means around 1600 km per second. So that was a bit alarming. In fact, I was not really working in this field. I just did out of curiosity that can I find out the velocity of the solar system this way. And this value came high. So I sat over this result almost 5 years. And every few months I'll pick it up, again check, go through again thing and try to do it. I generally use IDL. Then I learned MATLAB and some other, I thought maybe some problem with the computing system. Any case, but I mean nothing doing, everything was giving same value. All right. Now, you can get also dipole direction, and it turned out that dipole direction, at least in NVSS, was within 1 sigma almost, within the CMB dipole. So that was even more strange. Although it was also a bit comforting that means something, see, by, as we say, by mistake, you cannot bring it same direction because there are so many options. It could be any direction sky. But if it is coming to that direction, there might be something genuine in that. Although magnitude being 4 times what was a bit alarming. Anyhow, this is, I just give, the method is very simple. Shabbir had yesterday told how you get dipole D, and actually suppose you choose certain direction and you assume that there is motion in that direction, let's say CMB itself, then divide the whole sky into 2 hemispheres, one centered on that direction, other opposite, and then you just count the number of sources in that and number of sources in the opposite hemisphere, and then you get the dipole this way. Now, as I said already, the NRO NVSS gave, which has 1.8 million radio sources, it gave a value which was 4 times the CMB value. Okay, just. Now, there have been subsequent findings which also show that the value of dipole motion, dipole anisotropy, is much larger than the CMB. In fact, none of them has given a value which is as big as CMB, or at least not given uncertainties which fall close to CMB. But most of the directions are in a narrow range around CMB. So that is still surprising. Like this is NVSS dipole, and see, this is a contour map. Radio astronomers or others, they'll easily understand contour map. For any case, in this contour map, I have actually taken the sky, divided it into 2 by 2 degree pixels, which is, gives you 4 pi steradians give about 10,000 pixels, 10,360 pixels, and then determine for each of them what will be the dipole by dividing into hemispheres. Okay. For each is different hemispheres, of course. And then we get the dipole. Actually, these units here, this one is in CMB units. Okay, if you are getting 1, that means you will say that you are getting same dipole as the CMB. So to recognize it easily. So we are getting actually around 4 here, 4 times the CMB. This is the CMB dipole direction, and this is the dipole direction which turned out for NVSS. This is recent determination by Subir told yesterday, which is also actually close to this see largest contour 4. Okay. Now, how do you zero down on this value? Because you could be anywhere in this. It could be close to this also. Then there is a way to do what I call 3D cos fit. See, if dipole is in certain direction, then the all other points in sky will give you component of that dipole in that direction. Let's say go down as cos theta. If theta is the angle between the 2 direction or actual dipole and the direction you are seeing, then you can do a cos theta fit, 3D cos theta fit to the whole thing for every point. You take every point and take the remaining n minus 1 points and make a 3D cos theta fit, and then see which give you maximum value. And also you can do chi-square fit, that where the deviation from the cos theta is there. So this is that, and this peak comes, which is, and this is the minimum of chi-square. Both are coming at same point, okay, and chi-square value is coming close to 1. Actually, is reduced chi-square, coming close to 1, which is the ideal case, as it should be. It's coming 1.2. So at this point, which I had shown here, it comes from that. Okay, so I don't know whether if you do something like cos theta fit to your, whether you'll get same point or something. Any case, these are not too distant, although if you look at this point, this is the 1 sigma errors as they had given. then this CMB does not fall within 1, in fact more like 3 sigma away from that. Okay. Now, yesterday in discussion, somebody was saying that how do you know that you are getting a correct value, whether what about nearby sources and other. So one way is to divide your sample into different flux bins and try to for different, because like I divided many flux bins, this is 50 millijensky and this 50 millijensky, and then you determine the array and declination of, by the previous what I showed, same you calculate the direction as well as the magnitude, and as you can see direction does seem to give the same value irrespective of the flux bin you are using, and even the magnitude seems to be similar, 1.6, it's units of 1000 kilometers per second. Also there is that what about nearby sources like Virgo supercluster. See, most of those galaxies, if you see the radio flux, it's of the order of millijensky or so, and here we are working minimum flux limit is kept 15 millijensky, much above the which normal galaxies are known to give flux. But in any case, to see that there is no effect of supergalactic, so I divided into supergalactic latitude cutoffs. Okay, first one is of course 0, that is no cutoff, and then 5, 10, 15, 20, and there is no change in the, if you go horizontally, there is no almost no change in the values. That means if nearby galaxy, at least in the Virgo supercluster system is there or around, that is not not affecting the thing. I'll just take some water. Actually, last night I had some slight fever. Okay. So this makes me confident that most of the result is not spoiled by nearby sources. Now, okay, after that, in fact, there was a meeting, Govind Swarup's 90th birthday in Pune 4 years back, I guess. And then at that time, just talking to people, I came to know that TGSS sample also can be used while talking to, it just occurred to me. TGSS is TFR JMRT sky survey. Now it's a different frequency than totally independent NVSS. Then I thought, okay, why not use this? Here, of course, I had to restrict myself to 100 millijensky and above. And then same thing as was done for NVSS, same thing is done here. And this, of course, is a CMB dipole direction, and this is the TGSS. Okay. Now, you added those 2 minutes. Okay. But here, you see the amplitude is coming 10 times the, earlier it was 4 times the CMB value, now we are getting 10 times, so that's even more alarming. Okay. And this is just plotted to show the two TGSS and NVSS versus what expected from CMB. And you can say they are well above noise. In fact, this is almost 8 sigma result if you trust it. Okay. Now, I have tried now the 2 new available samples, VLASS large sample and also RACS sample. Okay, the last one is with the Australian square kilometer array pathfinder, and both have about 2 million sources. And same thing I do in these. And here, this is VLASS survey. Here dipole is bit far, not bit, quite far from the CMB dipole, and the amplitude is about 4. See, this is the 4, this 4 times the CMB value, this contour last. Okay, this is RACS survey, and here, in fact, the dipole is quite towards the south, and this is the CMB dipole, and this is the RACS dipole. Well, these are observations. Okay, and this is about 7 times the CMB value. Now, all this is bit alarming, and there are now many dipoles are known. Firstly, of course, CMB. I have given Reionisation like condition coordinates, and NBSS, TGS, and also from mid-infrared things. These are DR12Q redshifts, WISE catalogs we yesterday talked about, and also you can actually see your motion can introduce in the Hubble plot a dipole, okay, and you can use that also to measure, and that is independent of any inhomogeneity matter density, okay. So that also can give you velocity, and these are of course VLSS and RACS today. Now all these, it may be difficult to see from that, but if I plot all these directions in sky, then all of this is CMB, okay, which is almost no error, and these are the other which are coming less than 1/6 of the sky around CMB. Now if there's random errors are there, or the systematics, any of these could have gone anywhere. So even if they are not coinciding with CMB, at least they are in a narrow range of sky. So that means there is some, either the sky, that part in sky has some problem or some peculiarity, which gives rise to these extra motion, or whether it's extra motion or it's actually extra density in certain direction. And of course that then one has to also take into consideration that even CMB, what we say is a peculiar motion of solar system, it may not be that. It may be the actual inherent some problem with the CMB, okay, some dipole asymmetry. So that's all. I can just, okay, same thing I just talked. These just different language, Indian languages apart from English, to say of saying Namaste, Vanakkam, and Namaskara. This is of course my mother tongue Punjabi. This is my mother-in-law tongue. My wife is from Karnataka. And this is Gujarati where I stay. This is my father tongue. My father knew Urdu only. Okay. And these of course Bengali and Assamese. And this is Vanakkam. Any case. Yeah.
Thanks. Maybe some.
Part of the scatter that you find between the dipoles from different surveys,
Okay, yeah.
As you said, they all cover limited regions on the sky.
Yeah.
So one has to be careful about the estimator used for the dipole. For example, that hemispherical estimator which you pointed out, that's the most robust, the simplest.
Okay.
You just count in. So we actually have done simulations to check how, if there is any bias in the estimator, and it turns out there is, both in angle and in amplitude. Of course, if you had infinite sources, then there is no bias, but for finite samples. So if you use a quadratic estimator, a least squares fit, then that's, we find, just empirically more robust, and this has also been used by other people. And then the discrepancy, some of the discrepancies disappear. Also, the TGSS catalog we find has, well, the survey had calibration issues. And you can actually see that
to
in the
be
data.
frank, even TGS when it gave very high value, I myself was alarmed. But my only source of comfort or whatever you can say is that direction was coming almost ditto there. Okay,
That's
unless
correct.
it is again chance. Okay.
But we actually looked at the TGSS catalog and found it just in a data-driven way that there is a calibration problem with that, which I think Intema et al. Agree with.
Like some people say, "Galti se mistake ho gaya."
No, it's a difficult thing.
It can happen.
Low frequencies is very hard to do such a thing. So I think that actually, as you say, the directions are all consistent. The amplitudes, the tables that you said are quite different, but some of those discrepancies could be due to some of these couple of reasons I've given.
Well, anyhow, this is just to alarm people that there is something more maybe involved, and they may have to have a look at the dipole. Pardon? Actually, to be frank, I have no interpretation. All I say is that, I'll say tongue in cheek that is there some axis of the universe, there is some particular direction. Why all of them, even if there are some mistakes, whether random or statistical, why in spite of all the mistakes, 9, 10 measurements are turning out to be same direction? Okay. Or that we are interpreting CMB, or our interpretation is due to solar motion itself is wrong. there is certain inherent asymmetry in the universe. And of course, when there was only CMB, then of course that was natural to expect or say that it is due to solar motion. But now there are many more things are coming, and if the magnitude differences are, even if partly they are genuine, then it cannot be due to solar motion. Solar motion will give only one value, right? Whatever may be your method and technique. So I will not say that I have answered to that, but I am just pointing it out that there is something is missing somewhere. Yeah.
Let's thank Ashok and other speakers of this session.
Great. So this session is going to be on 21 centimeters, specifically some technical aspects and some inference aspects as well. We first start off with Kanan. Please take it away.
So first, I would like to thank the organizer for such a nice conference and the excellent hospitality. I am going to talk about heating of the intergalactic medium and its impact on cosmological 21 centimeter signal, particularly on the global 21 centimeter signal. The work that I am going to discuss is mostly done by my PhD student Ankita Bera and Dr. Soumodip Samui, my colleague at Presidency University Kolkata, is also part of that. So as you know, the spin temperature can be calculated using this relation. So it depends on IgM kinetic temperature, background CMBR temperature, and also on the strength of coupling, two coupling mechanisms, that is Lyman alpha coupling and collisional coupling. So in order to calculate the spin temperature, we need to estimate IgM temperature during the cosmic dawn. And we know about the cosmic microwave background radiation temperature already. So now let's focus on the IgM kinetic temperature. So there are several mechanisms proposed in literature that can influence the IgM temperature during cosmic dawn. Here I list some of them, some important ones. So the most widely studied mechanism is X-ray heating of IgM temperature, and then cosmic ray heating, magnetic heating due to magnetic field, Lyman alpha photons, CMBR. I will focus on this cosmic ray heating part, which has not been studied in detail so far. So let's move on. We can calculate IgM temperature, evolution of IgM temperature as a function of redshift using this equation. So you see there are several terms on the right. So it depends. The first term is the adiabatic cooling. It's basically coming from the fact that universe is expanding adiabatically, and then there are heat flow from CMBR to the IgM through Compton scattering, and then the last term, which actually accounts for all the other sources of heating like X-ray heating, cosmic ray heating, Lyman alpha heating, and any other mechanism that you can think of. So let's focus on cosmic ray heating. So cosmic rays are generated in the termination shock of supernova explosion, and those supernovas are the end products of POP3 and POP2 stars during cosmic dawn. A significant fraction of supernova kinetic energy, that is around 15% of supernova kinetic energy, is gets injected into the cosmic ray energy. In case of supernova occurring in many halos, low energy cosmic ray protons, mostly with energy less than 30 MeV, they effectively interact with the IgM via collisions with the free electrons, and also it can transfer energy through ionization of neutral hydrogen. High energy protons, they don't interact much with the IgM because of the less cross section, but they can still travel into the intergalactic medium, gyrate around primordial magnetic field, and generate Alf-Band waves, which gets damped, and that's how it transfer energy. So for the first mechanism, the total kinetic energy injected per unit physical volume can be estimated using this formula. So you see, it depends on the total kinetic energy of supernova. It also depends on star formation rate density, because stars are the sources that eventually converted into supernova, and then supernova, and from the supernova energy is injected into the cosmic ray. So you need to calculate star formation rate density. Right. Now we need to model cosmic ray protons. So cosmic ray proton spectrum can be modeled as power law in momentum space like this. And here you see n dot 0 is the normalization factor, which we decide from the fact that certain amount of energy gets injected into the cosmic ray proton from the supernova. Then we can calculate the heating rate due to the cosmic ray protons due to the ionization, and that is the formula. So let's look into this. So this dEdz is the rate of loss, energy loss of cosmic ray protons as a function of redshift. NCR is the number density of cosmic ray proton in the momentum range of beta and beta plus d beta at redshift z. One important fact that we have to remember is that cosmic rays actually they propagate long distances and they lose energy while traveling. So we have to consider not only cosmic rays that are emitted from at redshift z, but also we have to consider past cosmic rays. So this equation basically shows how how momentum is changing, changing with redshift. There are two processes by which cosmic rays can lose energy. One is collision with the free electrons, and another is ionization of neutral hydrogen. So we can use this equation to calculate the rate of energy deposition. And then high energy cosmic ray particles, as I said, they don't interact much with the intergalactic medium, but they can gyrate around the magnetic field and generate Alfvén waves, which then gets damped and energy is transferred. Okay, so now let's talk about star formation, because it is also an important factor in this calculation. So we have considered POP3 stars and also star formation in atomic cooling halos. For population 3 stars, they were likely formed in mini halos with virial temperature in this range, and the cooling channel, relevant cooling channel is molecular cooling channel, and they are formed in metal-free environment. They are massive, luminous. We have also considered Lyman-Warner feedback. So basically, when stars are generated, they emit a lot of Lyman-Warner photons, and then that dissociates molecular hydrogen. So in that sense, they provide negative feedback to the population 3 stars. We have considered that, and we use Sturman mass function to calculate the halo formation rate, which is actually related to the star formation rate. And then for star formation in atomic cooling halo, we have adopted a model from Samir et al. 2007. So basically, this model has several mechanisms included in it. One is this galactic outflow parameter, that is n omega, and also so there are several parameters which are actually, so this model is calibrated using low redshift data and then extrapolated to high redshift. So this right panel shows the star formation rate as a function of redshift. Red one shows the star formation rate due to POP3 stars, and dotted blue line shows the star formation rate due to POP2 stars. And you see, as expected, star formation rate is dominant. POP3 star formation rate is dominant at earlier epochs. Then those POP3 star formation gets reduced because of the Lyman-Warner feedback.
but then POP2 star formation takes over. So the total star formation rate is shown in the solid black line. So if we plug in everything, and then we this is the result showing how IGM temperature is changing as a function of redshift. The red solid line, it shows IGM temperature. So initially, as expected, it will follow 1 plus z square, that is the adiabatic cooling. But then when cosmic ray proton heating becomes dominant, you see this, it is rising very sharp, and yeah, and it crosses the background CMB temperature at some point. Of course, there are many model parameters which are very uncertain. So this is not very. So this can change a bit, right? And then corresponding this solid dashed red line shows the corresponding spin temperature, because that is the one which actually influences the 21 centimeter brightness temperature. Okay, now. So in comparison, we also considered X-ray heating, because that is the most widely studied mechanism for heating. So we have adopted this model for X-ray heating from this paper, O3 and Thiet's paper. So we plotted the X-ray heating part also. So we have, if we consider only X-ray heating, the result is shown in blue line, solid blue line, and we see that X-ray heating and cosmic ray heating are comparable. So that is very interesting. And then this dashed blue line shows the spin temperature. So the point is that I want to make here, that cosmic ray photon can be a potential source of heating during cosmic dawn, and we need to investigate more in order to actually study its impact, right? And then there are several other mechanisms by which IGM temperature can be influenced. Another one is magnetic field, primordial magnetic field, and a lot of work has done by Sieve and Kandu and his collaborators. So there are two processes, ambipolar diffusion and decaying turbulence, by which you can actually change the IGM temperature at earlier epochs. So this plot actually shows IGM temperature as a function of redshift for if you include magnetic primordial magnetic field. So if you consider magnetic field with present day value of 0.5 nanogauss, then this red line shows the IGM temperature evolution, and you see this IGM temperature is much more than the background CMB temperature, which is kind of which is not the case, because we know that IGM temperature is lower than yeah, if you believe Aegis result, then you know that IGM temperature is much lower than the CMB temperature. So if we restrict that, if we put the condition that IGM temperature is lower than the CMB temperature, then the maximum magnetic field present day value should be less than 0.4 nanogauss. And also we show, just for demonstration purpose, that if we consider cosmic ray heating, then it can actually is very consistent with the Aegis result. If we include cosmic ray heating in addition to dark matter baryonic interaction, that process actually helps to cool down the IGM temperature below the standard one. So that's just a demonstration that cosmic ray can also be a potential source of heating. So just to summarize, that cosmic ray photons can be a potential source of IGM heating, and heating is comparable to X-ray heating, and different mechanisms that are connected to star formation, they have similar trend, like similar IGM temperature. So rising slope is very similar in all these processes, because they are all connected to star formation. So it will be very difficult to tell from observations, at least from global observations, which mechanism is dominant and which mechanism is subdominant. So maybe we have to look at the power spectrum and see if there is any unique signature for cosmic rays. Thank you.
Thanks a lot, Kanan. I had a very quick question on the magnetic field constraint you get. So on what scales typically is it? Because we do have more constraints on intergalactic magnetic field from, say, filaments, and those are on MPC scales.
This is at very large scales.
Megaparsec?
Yeah, yeah, more than megaparsec. Large scale cost. IGM, yeah.
It's very interesting, this cosmic ray heating, the early cosmic ray heating. One question though, the cosmic ray protons themselves, the usual mechanism assumes that the supernova blast wave, I think, moves into an ambient magnetic field. So is there an assumption that these mini halos do have an initial magnetic field, and if so, what strength would that have to be?
Not any assumption on magnetic field, but the way we think that when a supernova occurs in mini halos, shock front immediately becomes more than the virial radius, so it can easily escape from the shock front. So that, because it's a very small halo, so it can easily escape.
If not, let's thank Kanan again. Great. Next up, we have Samir.
Okay, so today I'm thanks the organizer for giving me this opportunity to present here. Today I'm going to talk about the pattern of primary beam non-redundancy in the closed back interferometers, mainly for the Hera. So without an introduction, just what is the redundant calibration? The visibility is basically measuring the Fourier transform of the sky brightness temperature fluctuations at two antennas, basically a pair of antennas, and if the distance and angle of this vector is the same, it basically measures the same Fourier modes of the sky. So using this concept, measuring the visibility at different pairs, using the same sky signal concept, same sky signal in all the pairs, we can calibrate the antenna properties, basically the gains. So this is the algorithm for the calibration for the Hera. Now, in reality, it may not be. There are a lot of things can happen. It might be that antennas are not physically at the same separation. There might be some difference between two pairs, and also it's maybe difficult to construct the antennas the same way. So basically, the primary beam pattern might be the different for the different antennas, and also the position error of the antenna aperture. So there are a lot of things that can happen, and due to these reasons, we are expecting the signal should be the same at two different antenna pairs, but it may not be. So in this study, we analyze the primary beam pattern of the different antennas and how it affects the measurement. So due to this non-redundancy, what can happen? So this is one of the simulation result of the Hera, and in the left panel it shows the power spectrum in cylindrical power spectrum. When there is no error, the foreground is located in this wedge shape region, but when there is position and beam error, the foreground lit in the UR window. So this is one of the simulation study. So the area of the 21 centimeter signal may affect due to this non-redundancy, because when we are doing the calibration, we are assuming the signals are redundant. So in this study, we study the effect of the primary beam non-redundancy for the Hera. What we did the simulations for the primary beam and different types of primary beam we considered, for which the antenna is the response function is different for the different antennas. So here in the black line, it is the actual antenna primary beam. But what we did, on top of that, we introduced some perturbation, basically the side lobe perturbation here. So assuming that the main lobe is same, but the side lobes are different for the different antennas. Another case we considered that this main lobe is different, but the side lobes are same. And another thing, the straight, the whole beam is straight. So there are a lot of possibility can happen, but we don't know what is the actual thing. So that's why we consider all the cases, and in here we consider the beam is elliptic and rotated. So a lot of cases we considered, and for the simulations we took 10 antennas in a hexagonal shape, and simulations we used Gleam catalog,
And here in the gleam catalog, there are some blank region in the sky. So what we did some simulations to fill this gap using some using the source from field region. We put the number of sources from this region to the blank region, and we fill the gap. So that is, and also we added the diffuse sky model, and also we add the noise and antenna gain. So lot of so all the realistic simulation we did for this setup, and this is the frequency and LST range for this simulations. So after introducing all the perturbation and all the simulations, what we did, we used the redundant calibration in this package. So assuming this the antennas are the redundant and applying this calibration, and after calibration we did the power spectrum measurement. So now I will show some of the results that we got from this non-redundancy, basically the non-redundant array. So in the left panel, so what will happen if it is perfectly redundant? We expect all the visibilities in that pair, basically in that gap or that separation, it should be only defined by the noise and only the no pattern. So basically in that black line, we show basically this is the visibility variance of the all the antenna, all the visibility in particular redundant group. It is 14.6 meter and it is 0 degree the angle. So that redundant group, we took all the visibility measurement and calculate the variance. So what we expect, it should be noise-like and the sky signal should be same. In the black line here we show when there is no perturbation in our simulations, and it expect like that. It is basically the noise-like. Then we consider different types of perturbation that I told, the side lobe perturbation or the main lobe perturbation. When you introduce perturbation, the variance increase. So here in the right panel, we show only the point sources, but the bright sources are not present in the data. In this panel, we showed the bright source, all the point sources are present. Now you can see, due to the non-redundancy, we get some feature here. Basically, the variance increase in this LST range. I will show some of the figures later why. So basically, by introducing the non-redundancy in our simulations, and after the basically this variance is increased when the point sources of bright sources are present in this range. And so this is just the feasibility simulations, no calibration and nothing. Now, when we introduce the calibration redundancy, we see the pattern is reduced. Some of the patterns, basically the variance is decreased in this range, and this is for the diffuse and point source. So the variance is increased when we add the point source and diffuse. So what the conclusion here from this plot? So the non-redundancy in our simulation introduced some feature in the visibility measurement, and it depends on the source, depends on the sky distribution. So here to study why these peaks are arising, so what we did here, we simulate, basically we show the track of the sources coming through the main lobe, and this is the all the sources, the bright sources coming in this main lobe, and here we show the basically the as a function of LST, what is the flux of these point sources. So in this range, basically in this LST range, there are some bright sources present in our main lobe, and due to this, the non-redundancy increase in this simulation. Basically, the variance increase. Now, when we apply the redundancy calibration, this effect reduce some factor. Basically, so this redundant calibration is reducing the inherent non-redundancy when there is some non-redundancy present. So this is the study that we did in our using these simulations, and this is the next result in these simulations. Here we show the gain of these different antennas, and this is the time versus frequency plot, and this is the color bar shows the gain, the fractional deviation of the gain with respect to the true gain that we have introduced in our simulations. So this result for the different types of non-redundancy that we introduced in our simulations, and we see that the difference, the fractional difference is increased and there are some bright sources in this present in the main lobe. So basically we are trying to solve the gains using redundancy calibration. When there are bright sources are present, these gains are disturbed due to the redundancy calibration. The gains are disturbed, and this is the fractional deviation of this gain is increased when there are bright sources in the present. So this is another metric we have introduced to study the non-redundancy. So the first metric we introduced is the variance. The second metric we introduced basically the gain of different antennas as a function of time and frequency. Next, there is another metric that we considered is basically the decoherence factor. What is this? We take all the visibility in that redundant group, and we are making the power spectrum from each visibility pair, and we do the two kinds of averaging, incoherent and coherent averaging. So basically the incoherent averaging, we are measuring the power spectrum first and then take the average. But in the coherent averaging, what we are doing, we are averaging the visibility first, all the pairs, and then calculating the power spectrum. So if it is perfectly redundant, it should be 0. So basically there is if it is perfectly redundant, all the power spectrum should be same, all the visibility should be same. It will not depend at which place we are averaging, and it should be 0. So this is the result of this decoherence, the metric that I showed as a function of LST. So what we showed here, basically this is the calibrated visibility power spectrum, basically the decoherence factor as a function of LST range. And here we see that on this range, this LST range, it is non-zero values. That means there are some decoherence happening due to this non-redundancy in this simulations, and this is the same thing, but here the true visibilities are there, no redundancy and basically no non-redundancy present, but we are not doing any calibration. So if you see the number here, it is 12% the decoherence, but here it is 2%. So that means that when we are doing the redundancy calibration, it reduces the non-redundancy as when the bright source is present, all the non-redundancy factor goes into the gain, and it is behaving like a redundant array, and the factor of the decoherence, factor of the non-redundancy decrease. So it's basically the decoherence factor, basically the non-redundancy is reduced when we introduce the redundant calibration. But if you see the features in the before the calibration, it was like a uniform shape here. But when you introduce the calibration, redundant calibration, we see some double-like feature. So we try to study why this is happening. So this is another simulation paper from Dillon et al. And here they showed that there are some double-like peak present in the simulated data when there is a bright sources present for next A, and due to this, when it is coming to the main lobe, so this y-axis is measure of the chi-square, how much difference from the true visibilities. So when this source is present, the difference is very less because this calibration is reducing the difference. But when the side lobes is present, this is not able to calibrate properly. There are some double peak features present in that due to the bright sources when it is present in the side lobes. So these two peaks are for the two side lobes. When it is passing through the main lobe, here it is the factor is less. But for the picto A, it is not going to the main lobe. It is going to the side lobe. There is only one peak present. So this we are seeing the same features in our simulations. So just to show that in our simulation there are some bright sources in the main lobe, and that's why the variance increase that I showed here in that region, and also the decoherence factor that I showed is reducing the factor is compared to true, basically due to the redundancy calibration, and there are some double peak feature due to this when it is coming to the main lobe and side lobe. So this is present in the real data also. This is the real data here, power spectrum, basically the power spectrum, and you can see there are some 5% non-redundancy present in the data, in the power spectrum. So we study the UR power spectrum also using some power law, and we see that this factor is
this non-redundancy is less than 5%. So this is much lower compared to the other systematics, for example, the coupling. So this is the whole thing that I wanted to say. So the redundant calibration, so basically the non-redundancy is present in the data, and we are trying to the redundant calibration using this configuration. And when there is a bright sources, the variability of the visibility is absorbed in the gain to give the illusion of the greater redundancy. And we show that this power spectrum is mostly less than 5%, and it is there are some features as a function of LST. So this is the study that we did.
Yeah, just a couple of quick questions. The first thing was the beam perturbations itself. So along the spatial directions, there were lots of perturbations from antenna to antenna, but were there also some variations in the frequency direction? That was the first question. And the second is, when you're looking at the non-redundancy, you're looking at the metric which is our tau 0, which is basically foreground dominated metric. Yeah. But you're also injecting the power spectrum and looking at the decoherence exactly at the 21 centimeter power spectrum in the last slide. So how well do they agree with each other?
Okay, so this is at tau equal to 0. This is the factor. But this 21 centimeter power spectrum, we are this is the compared to the true power spectrum all over the delays and all over the time. Okay, so that is just the metric how much non-redundancy present. Now in this plot, all over the delays and all time we studied, and so this is mainly the feature present on the bright sources in this region. So it's just the deviation is much larger compared to the true. And the spatial, okay, so this the frequency perturbation, yeah, we did another analysis, just the primary beam perturbation along the frequency. Yeah, that will affect also. So that we started in that similar order. Yeah, so it will introduce some pattern in this tau. Yeah.
I'd like to ask a question. So if you're able to absorb the non-redundancy in the gains when bright sources are going over, can you then transfer over that knowledge to observations where there isn't anything bright going over, or is it just not as simple as that?
So basically this is, okay, so this is the redundancy calibration is doing that. So it is inherent. So we don't have any idea of that how. So this redundant calibration, this gain is automatically absorbing the non-redundancy factor. So that is the inherent to the calibration process. So if you want to apply, if there are some non-redundancy present in the array, when you are applying the calibration, it automatically absorb the non-redundancy. So it's the assumption is that if the sky is dominated by a single bright sources, then it will absorb. Otherwise, it will be difficult to absorb the discrepancy in the gain term. It will only affect when there is bright sources. At that time, the gains, the discrepancy will be absorbed by the gains.
I see. Can you then transfer that knowledge to other observations?
Yeah, so that will we have to study that how much non-redundancy present and also the brightness of the sources.
Right.
So that will
right. That yeah, that's a limiting factor.
In Hera currently that is actually being transferred, so all the upper limits are actually blown up by the percentage of non-redundancy that's obtained from this.
Great, let's thank Samir again. All right, next up we have Madhurima.
Hi, I am Madhurima. I am currently a postdoc at Arka in Open University of Israel, Ra'anana. I'm working with Professor Salim Zurabi and other members of the ROFAT team. So today I'll be telling you how we can make a neural network model to infer IGM properties from 21 centimeter power spectra. So to begin with, this is a very familiar picture that we've been seeing throughout the conference. So we're particularly interested in this particular range where the first stars came into existence and eventually realized the entire universe. So the observations of the 21 centimeter H1 signal can either be the sky average global signals, and the experiments are EDGES, SARAS, Beacon, SciHy, LIDA, REACH, to name a few. And we have the 21 centimeter power spectrum experiments, MWA, LOFAR, GMRT, HERA, SK, ARTFAC, NENUFAR. So what we would like to know is that from these observations, how well we will be able to constrain parameters, the astrophysical parameters or the IGM properties. So why do we need an IGM based framework? This is a slice from a simulation called Grizzly, which is a 1D radiative transfer simulation. Usually in most of the simulations, we have the source properties like escape fraction, star formation rates, virial temperatures, minimum halo mass, etc., and a lot more other parameters which are used to generate these simulation boxes. So from these simulations, we compute the 21 centimeter power spectrum. On the other hand, the IGM needs to be characterized. These are more of the physical state of the IGM at a particular redshift, a particular state point of ionization. So we have these parameters like the ionized fraction, the morphology, which can be described in many different ways. We have Lyman alpha histories, thermal histories, etc. So these properties are not directly constrainable by the existing models, and so ultimately we need to find a connection between these IGM properties and the source properties when we actually have the 21 centimeter power spectrum observations. So how will we be able to extract the maximum information from these 21 centimeter power spectra is the question. So characterizing the IGM properties can be a bit tricky. So in our work, we have just considered the one particular redshift at redshift 9.1, and we have considered the ionization fraction XH2 and a bubble size distribution. So this bubble size distribution essentially is gives an indication of how the morphology looks at that particular redshift. So over here you can see that there are these black regions which are the bubbles. So until the bubbles overlap, the mean free path method which we used, that is pretty good to characterize the IGM. So now I'll tell you a quick summary of how ANN works. I'm sure most of you already know how basic ANN works by now. So essentially in a feed-forward network, we have neurons, input neurons and output neurons, which are all connected with each other, associated with a weight and a bias. So an error function is computed, and there are multiple iterations where this particular error function is optimized until we achieve the results that we want. Now, in supervised training methods, what exactly happens is we already give the network an input and an output, and we ask the network to find the connection between these two. So in our case, what we are doing, we are giving the ANN model the power spectra, and we are training it to be able to learn the connection between the power spectra and the IGM parameters which we wanted to learn. So and the training process is carried out by the back propagation of errors eventually. So we have a large data set. We split it up into training and testing sets, and after a few rounds of validation checks, we finally confirm that this is the model that we will be able to use for a particular kind of data set, and maybe outside that as well. So once we are sure of our model and we are happy with our accuracies, model accuracies and performances, we use that model for our other work, other predictions. So this is how the training set looks like in our case. Over here, these are the bubble size distributions, and we have the corresponding ionized fractions. We have taken the simulations from the Grizzly, using the Grizzly simulation, where swing temperature fluctuations are not considered, and these are the source parameters associated with the set of simulations which we have used. We have used around 7,000 training samples in our work. So essentially what we do is we input the bubble size distributions and the ionized fractions and predict the power spectra. This is a simple flowchart showing the same, inputting the bubble size distribution and XH2, we get this as our prediction. So when we look at a model, we usually look at how the loss function has evolved over the epochs. So you can see that the loss has minimized quite well, and we have a high accuracy of around 96%. So these are the predictions from the ANN. Once the ANN has been trained, now we give it an unknown bubble size distribution on XH2, and we predict the power spectra. So on this left plot, this is just a ratio between the predicted power spectra and the original power spectra corresponding to their respective K modes. So you can see this is a set of around 1,000 samples. So most of them are limited to, they have been predicted almost accurately where the ratio is around 1. On this plot, it's an overplot of the R2 scores per K mode for these particular test sets. So once again, you can see that the R2 scores are mostly centered around 1, which means that the predictions are pretty good. So now that we have this ANN ready, we would also like to use this particular model in an MCMC framework to see how well our parameters can be constrained. But there's a catch, because the bubble size distributions which we were using to train our network, so those were functions of R. And there are a lot of points over there, like more than 300 parameters in this particular case, and the ionized fraction. So MCMC will not be able to handle such a large number of parameters. So what we do is, we parameterize the bubble size distribution as a log normal distribution, and we reduce the parameters to only mu and sigma, and we use the particular ANN model to run the MCMC framework. So what we find is that these are the values for one particular observation from the Grizzly model, where we have assumed 47% ionized. So these are the true values of the parameters, and we see that the MCMC constraints are quite in agreement with what we expect. So next thing which comes to our mind is, how well would an ANN be able to predict the same parameters using given an unknown power spectra? So over here we see that even if we separately train another ANN with a power spectra and we are predicting these IGM parameters, they also predict quite well. We achieve accuracies of around 98%. So a quick comparison between the MCMC values predicted and what we get from the ANN predictions, we see they are quite in agreement. Not only that, but the only catch is that MCMC takes a lot more time. The ANN prediction happens in 1 second, less than a second, for the kind of data sets that we have considered. So this entire analysis is just limited to one redshift. We plan to extend it to a range of redshifts and including more different models. So in the first slide, like I showed, that there should be some connection between the IGM parameters and the source parameters as well. So we also try to train an ANN to find the connection directly between these IGM parameters and the source parameters, just as a check. So this is what the training set looks like. We have the bubble size distribution, and this color bar is the ionized fraction, and these are the corresponding zeta and minimum halo mass from the same set of Grizzly simulations. So we say it's not very good, but there is a good amount of, the R2 scores are like 96 and 98 for the test set which we have considered, but there are these particular values where there is a constant kind of prediction for a range of parameters. So if we work on this even more, like trying to include models which will have more distinct features, maybe we will be including more IGM parameters over here and more source parameters here to see what kind of mapping can be found using them directly. So that's all. I will wrap up here and I'll take questions if you have any.
Thanks, Madhurima. We have time for questions.
Thanks a lot. I always have curious when looking at ANN or deep learning or something, that how are you, I mean, how confident are you that, for instance, this bubble size and the other parameter you took are the main, contributors to what you're seeing? So for instance, could there be some spurious correlations with other parameters degenerate with these, which you don't pick up just because of the ANN being trained on a certain set or a certain framework? So have you explored this, or is there?
No, as far as this IGM parameter set is considered, the bubble size distribution takes into consideration the distribution of different sizes of the ionized regions that are present there. So other than that, we have the ionized fraction. Of course, there might be other parameters as well, but we are trying to see how well only with these few parameters we'll be able to constrain them and find the connection between the power spectrum. Thanks.
First, was this all done at the single redshift? Is it
Yes.
true? Okay.
At 9.1.
Now, so you're trying to connect different types of parameters, but the question is whether that is dependent on the particular method that you're using for simulation. So I was wondering if you're planning to try to infer this from Grizzly, from one type of simulation, and try to see whether it works for a different type of.
Yes, yes. Actually, we have done that. Maybe I have one slide. Yeah, it's not very good, but these are the predictions from C2 ray simulations. So you can see for certain power spectra it has been retrieved, but I cannot say that it has been predicted very well. So to take into the point being that C2 ray models are slightly different from what we use in Grizzly. So we are trying to, we use the same kind of density field and calculate the power spectrum in the exactly similar way as we do it for the Grizzly simulations. But I think still the bubble spectra and the power spectra, bubble size distributions and the power spectra are not exactly similar to what we have trained it with. So we need to make our training set even more vast and include some more parameters like Hamza pointed out. So we have one or two parameters in mind which we might be including so that we will be able to predict the other simulations also well.
Thanks. It's good to see these results. So I was the bubble size distribution is not a quantity that is uniquely defined.
Yeah.
There are various algorithms that can be used, and it's because the geometry of the H2 regions is very complex. You can't actually. So what method did you use?
This is the mean free path method.
Okay. So it could also be worth maybe exploring another method to define the bubble size and see how sensitive the method is to that.
Yeah, it's like a lot of different methods are there to actually quantify it. So we can't really say which one is better at this stage.
You can predict from your network, but the thing is that can you predict also the statistical significance of this prediction? Is how accurate like the error bar on those predictions?
Yes, like if you see if you consider that these are the parameter values which are predicted from the neural network, they have been predicted with a 98% accuracy. So we can translate this particular error which we get here per parameter to the predictions, and that is evident because given the same input to the MCNC framework and to this particular ANN framework, we have got almost comparable results. Other than sigma, the other mu and XH2 are almost similar. From the MCMC plus, you definitely get a exact constraint on the errors and with how much confidence we get it. But I think that the errors are translated into the predictions. I mean, that is how we, or as you know, we can put a single error and we increase the amount of noise and do some kind of, add some kind of bootstrapping to get a particular error on the energy.
Yeah, you are showing the predictions, the power spectrum predictions from your NN model compared to the true, and they were deviating by few percent to 10% and more.
That was for C2 ray.
No. I mean, in your talk, there was this red, blue.
Oh, yeah.
No, the power spectrum predictions.
Okay, yes.
As a function of K. Yeah, that one. So, do you have a feel for how, how large these deviations are compared to, say, the cosmic variance or the error bars in a typical experiment?
No, not with cosmic variance, but like when we try to look at these particular models which are having this large deviation, we found out that these are sort of the extreme models in that particular training set, which has a very different kind of power spectrum compared to the rest of the power spectra in that particular set. So we have to see the comparisons otherwise, but over here we have not considered any effect of like cosmic variance and how it's affecting.
Great, let's thank Madhurima again. Next up we have Rajesh.
Okay. So first I would like to thank the organizer as well as RRI and SODA for, so I am visiting RRI with this conference. So thanks for all these things, all this arrangement. And yeah, so I would like to talk about precision cosmology with 21 centimeter signal from dark ages, and this work was done with Rajan Barkana. Rajan Barkana, so thanks to Rajan, so we have already have a overview of this topic. So now I'll show some of, so I'll reiterate those things, but I'll show some of the new or details of those results. So this is the outline. So I'll briefly tell you about the expected signal, then the problem we are exploring, and the motivation behind this problem, and some of the experiment I'll show, but not in details. Mainly I'll focus on the method and the results. All right. So we are focusing on the dark edges, and we can write down the brightness temperature using this formula. Again, we haven't included the Redshift space distortion factor and all these things, but again, so this is the expected signal we will get. All right. So the problem we are focusing is can we use the dark edges 21 centimeter signal, both the global and the power spectrum, to study the cosmology. I'm talking about the standard cosmology, not any exotic models. Basically, can we use this signal to constrain the cosmological parameters? That's the problem we are focusing. Or in other words, we can say, is it possible to observe, or is it observation feasible to do this type of to study this problem? See, so as theoreticians, we can predict or we can study the feasibility of, or we can say what is the minimum requirement to study this type of problem. So that sort of thing we can do, and the people should look into this calculation. It is like a baseline calculation, and design or spend money on something that they want to do. So this is the motivation. So as you know, it's a clean probe like the CMB. We can so there is no sources of light, so it's free from astrophysical processes. It's a clean cosmological probe. And unlike CMB, however, we can probe this 21 centimeter signal in a 3-dimension volume. That makes so we can have large information over a wide range of redshift or time. So that makes it very interesting. And we don't need to use any complex nonlinearity included in our model, because the field is linear, and it has been shown that it is sensitive to so the power spectrum is sensitive to these cosmological parameters. And there are some geopolitical context here, but I am not going into those things. If time permit, I can discuss. Okay, so now the method we are using. So we are focusing, as I told you, we are focusing on shape case, that is the standard cosmology, and trying to constrain the lambda CDM cosmological parameters using this global signal and power spectrum. So as it has been shown that for global signal it is easier, and we need a well calibrated single antenna, and that is why it's relatively simple than the power spectrum. For power spectrum we need large arrays to study this dark ages 21 centimeter power spectrum. For power spectrum, we use CAM to get the basic power spectrum, but you see, we want to be very precise. Means we want to be very accurate in our modeling and all these things. So we include distortion due to peculiar velocity and Alcock-Paczynski effect and light cone effect. So we don't want to we want to include everything to our model. So that's why we did. And for power spectrum, there is another complication is the angular resolution. So for a given antenna distribution, we cannot achieve higher and higher angular resolution. So we have to restrict our angular resolution. That we have also included in our modeling. And as I told you, this is just the baseline calculation. So we haven't included. We assume that the foreground has completely removed. So we haven't studied the foreground and in this study. All right. So this is the expected signal with a minimum of around minus 40 millikelvin, and it peaks around 75 Redshift. And this shows these two curves, the dotted and dashed curve shows the expected noise for thousands and 100,000 hours with delta ln nu 1 basically. And as I already discussed, we need so there is this. So we are talking about very low frequency. So we need to place our telescope or instrument on the moon or on a space-based experiment we need to design. So that is why there are quite a few proposal, or there is already instrument. Yeah, so I will not go into those things. Now from this global signal, we can basically, so the parameters is basically sensitive to the amplitude of the global signal. So, and the parameters are this omega matter and the omega baryon. And as you can see, if you can see, there is a large degeneracy between these two parameters. So basically, since I told you, there is a single quantity where that is the amplitude of the signal, and that is why basically it's effectively one parameter, right? So, but still we can do better. So we can constant a combination of these two, and we define, or we can find this combination using this formula. And you can also calculate this. Means you can get a flavor why we are getting this type of form from the equation that I have shown in the first slide. That is the brightness temperature equation. So this is the parameter. We can so the variance in this parameter is minimum, and we call it C global. And this shows the, so for thousands hours of integration, we can get up to like the 5%, 5.5% relative error. And if we go like 10,000 or 100,000, it will scale as the time. So other than this, you may ask that the noise is, the error bar is very large. So is it a good parameter to study? So that's why what we did, we ran a MCMC to see whether we can whether we have removed the correlation that we have seen in the previous plot. And as you can see, since the errors are large, and after this MCMC run, the errors almost gone, the degeneracy almost gone. And so this parameter choice is good. And in addition to this C global, we have also considered the fraction of the baryon mass in helium, as well as the total mass in the neutrino. And yes, the global signal is particularly sensitive to this YP parameter. However, it's not very sensitive to this neutrino mass. Using the global signal, we can for the 1,000 hours of integration, we can achieve like 11% relative error in this on this parameter. Now the 21 centimeter power spectrum. So this shows the 21 centimeter power spectrum. So here the solid lines are the power spectrum, and these dashed lines are the defined noise. This noise include both the cosmic variance and the thermal noise. So, and this is for the configuration A. So configuration A, here this collecting area is 10 kilometers square, and the integration time is thousands hours of integration time. And so this is the A. this small short dash line is for the configuration A at two different configuration A, and the dash line is for the configuration B for two different time, and this dotted line is for the if we include the angular resolution in your calculation. So you can see you cannot achieve. So it's basically smooth version of the power spectrum. So this is the power spectrum we will observe for a given set of antenna distribution. All right. So now, as you can see, this is the same power spectrum as a function of frequency, and the same noise curve. As you can see, up to redshift of 40 we can go. So the most of the information we are getting is below 50 actually, and the higher basically means there is no information we are getting from the lower and lower frequencies. So that's the point. Most of the information we are getting from the lowest frequency basically. And as I told you, it needs the power spectrum needs a great investment and resources compared to the global signal. And here are a few examples. And all right, so so what are the constants we are getting? So this shows the parameter that we have considered in the Fisher matrix analysis, and these are for the different configuration that we have considered. However, we haven't shown the configuration A because the errors are very large, so it will shoot outside. So we can, for the configuration A, we can only constrain the C. I'll show you, but for the timing, just consider these three. So as you can see, this is the Planck. This orange bar is for the Planck, and this is for Planck with BAO. So and as you can see, the error bars are quite large, like two orders of magnitude higher than the Planck prediction. I am not saying that we can achieve those high accuracy, but still we can do. So remember, these are independent of Planck, and if we combine all these things, we can still improve our understanding of the cosmology. And I'm not showing you the full corner plot for these all parameters because it will blow your mind. So I'm just want to focus you on the correlation coefficient. So this shows the correlation coefficient, and just you can see there are large degeneracy between the parameters here also, just like the global signal case. And this again we did the minimum variance to find the minimum variance parameter. So we find these parameters, and we can find the minimum variance for this combination, and then we can now for the configuration A, now we can constrain this C power spectrum, that is the combination, and this shows all the results that we have got. So as you can see, this is the power spectrum. So as you can see, for the 1000 hours and for the configuration A, that is 10 kilometer square kind of area, we can achieve like 5% percentage error on this parameter. And if we increase the integration time, or we can say the collecting area, we can improve. It scales as time basically. All right. So now this is the global signal. Now I would like to focus for this Planck YP parameter. So Planck can constant parameters like 8%. The error on the YP is like around 8% or so. But for the power spectrum, we can using the power spectrum we can achieve similar kind of percentage error on the YP parameter, and that is good. As well as for the neutrino mass also, so the configuration A is high 10%, but sorry 1%, but for other configuration we are as good as Planck basically. So that's a good thing. So we still have some hope. Now I would like to conclude. The 21 cylinder 21 signal from dark ages is an independent probe of the cosmology. And the problem is, can we constrain the cosmological parameter? And we have seen that yes, we can combine the parameters and constrain it. And the problem is to study this type of problem, the ionosphere is the problem. So we need to go to the we need lunar or space-based experiment. And there are other challenges. It's a active field of study like foreground and other things, instrumentation and all these things. So yes, there are challenges, but still doable. And the global signal, for global signal, 1,000 hours of indication time would yield a 5% error, and on a combination. And for power spectrum, we can achieve similar constraint using 10 kilometers square and with reasonable like 1,000 hours of integration time. And also we can constant we can put some constant on the YP parameter and neutrino masses also. Thank you.
Thanks, Rajesh. Questions?
So, given that we are struggling to put a 1 square kilometer array on Earth, how easy is it to deploy 10 kilometers,
yeah,
10
so
square
it depends
kilometers
upon
on
the
moon?
political situation. If countries are competing each other to go to the moon again, return to the moon again, and you see the space is now more accessible due to the startup and low cost airlines. So yeah, so it depends upon how much money you have.
But it's a lot of square kilometers.
Yeah, it's
what
a lot
I
of
was
square
wondering
kilometers,
about. I don't doubt that we can manage to
so
put
everyone,
something on the moon. But
since they are going to the moon again, so they want excuse. For them it's excuse, but for us it's science. So yes, we can push that you can build, like you can send robot to like deploy antenna and all these things.
But maybe it's easier at low frequencies.
Yes.
I was hoping.
And I'm talking about the back side of the moon, so quite RFI situation is low.
Can you go back to your neutrino mass constraints on the second last slide? It's actually quite intriguing. So your best case scenario, your error on the neutrino mass is less than 0.01.
Yes.
So you're saying that you will detect the minimum mass normal hierarchy with greater than 6 sigma. That's the most stringent. Do you know where you're getting the signal from? What?
Yeah. So
specifically about the power spectrum.
Let me point out one thing. So for these constant, we have considered other parameters are not varied. So we are assume other parameters are constant.
Okay.
And other parameters are not.
Because the neutrino signal is very degenerate with AS.
Yes. So that's so I think I have written somewhere, but I forgot to mention. I think. Yeah.
No,
so,
this is EV. I think the neutrino axis is actually EV.
Yes, it's EV. So I forgot to mention this. So I like to highlight that we fix the standard set of parameters.
For your YP and MU. I see. Okay.
Sorry about that.
Thanks.
So for the power spectrum case, are there any K values which are not accessible to other experiments but only for dark ages, like CMB, lensing, Lyman alpha forest? They cannot do it, but dark ages can do. I will just measure the power spectrum.
So you see, it depends upon how you design your baseline and all these things. If you want to focus on particular K mode, you just increase in the baseline, same baseline to measure that mode. So it's a how you design the mode. So it's accessible. You can access all the K mode, but it depends upon how large your baseline or how compact your arrays and all these things.
So won't that be a good science case to go to a K value which is not measured by other experiments?
Yeah, so BAO scales are...
BAO is measured.
Yeah.
But suppose we go to K equal to 10 or so, which is very difficult.
Yeah, so we need to place the very large distances.
So how viable
that? I don't know. Means there is curvature also, so I don't know how good it would be. Yeah. So, so then...
All right.
Yeah, or you can, if it is space based, you can place. So this is a core antenna, core telescope, and you can place those daughter telescope or very sparsely. Then you can do something. But again, it depends upon the.
All right. If you have any more questions, please see Rajesh at lunch. Sorry,
okay,
we ran out of time. Let's thank Rajesh and all the speakers today.
Yeah, thank you.
So in this session we will have two talks, and 6 poster talk. So the first speaker is Shadab Alam.
So I would like to start by saying thanking the organizers. I'm really happy to be here, and it's great to be celebrating 75 years of RRI. So today I'm going to talk about modeling the peculiar velocity around group, which is sort of very different topic compared to what we have been discussing so far. And I'll be talking about these plots in more detail as we go through the talk. So let me give you a slightly different version of this picture of the universe, which we have been seeing many times in this conference. So far what we have been seeing is as if we are some supernatural being and we are looking at the universe from some outside perspective. What this picture changes here is that we are here, part of the picture, which is today, and we are looking at outwards, looking at galaxy surveys, which has mapped significant part of the universe, and then looking at somewhat what we call quasars. These are galaxies with active supermassive black hole, very bright, so we can see it to very far distances. And then there is a region which is dark ages. We don't have many observations yet in terms of putting in this level of plot, and then finally we go to CMB. So this is all of our observable universe. And then all the pictures we have already discussed several times what happens, what is our current hypothesis to explain all of these observations, right? So in this picture, if you think about the current understanding of our universe, there are two key things. One is how much of the matter is in terms of dark matter. What is the total matter content of the universe, and what is the smoothness of this matter distribution? So that is represented by this picture of the road, whether the matter distribution is very smooth or very bumpy, and that is parameterized at sigma 8 parameter, which also we have seen. And so if you look at CMB and try to measure these things, you find very precise measurement just from CMB under the lambda CDM assumption. Now, if I want to try to measure the same thing through all the surveys in this low redshift regime galaxy survey, you again find measurement which is not as precise as CMB, but somewhat discordant with CMB, and there is a degeneracy in this measurement. So there is about 2.5 sigma based on purely looking at cross correlations of galaxies with CMB lensing, and there is even higher significant issue if you look at the weak lensing studies combined with that. So this is one of the things I wanted to highlight. There are many inconsistencies which are coming up at the 2 or 3 sigma level, and we are at the age where a lot of data is going to come. And so what I want to talk about today is what are the different ways to probe the same thing apart from what is already discussed. So I wanted to draw your attention to this effect called redshift space distortion. Several speakers have mentioned this very briefly, so I wanted to just describe this a bit more detail. If you're thinking about galaxy survey, right, these are tracer particles which are in our model view of the universe. They are living in somewhat dark matter halo, which we can't see, but we can observe the effect of it. And these galaxies are dynamic in nature, so they are not stationary. They are interacting, they are having party of their own, they are performing what we call cosmic dance, and so they will have peculiar velocity. And so because of this peculiar velocity, when we go and try to measure their redshift, which is the primary way we can measure precise distances to cosmological scale, you're going to see a part which is because of the cosmological expansion, and then you're going to see a component which is because of the peculiar velocity. This is a key probe of velocities of these galaxies. So what I'm saying is, if you can measure redshift precisely, you're sensitive to not just how far these things are in terms of expansion, you're also sensitive to what is the peculiar velocities of these things, which gives you extra handle on your theory. There are also higher order effects like gravitational redshift. I will be happy to talk more about that, but we'll be ignoring that for this purpose of this talk. So now what you're trying to think about is, when we are measuring redshift, that is how we are estimating distances, but these are not true distances. They are biased because of this peculiar velocity. And so if I sit on any of those galaxies and look at what is the nature of distribution of all the galaxies around me, the line of sight direction around which you have peculiar velocity component affected, that will introduce anisotropy, and this is what is called redshift distortion, and that's what is shown in here. In this picture, basically, we sit in each of the galaxy in our survey and look at what is the distribution of all the galaxies around that galaxy. So we go and do that repeatedly in the entire survey. And so this distortion is famously known as first prescribed by Nick Kazar. So this is what Kazar model in the linear regime. And this is basically what is the large-scale flow of galaxies around each of these galaxies. So that's what we are seeing here. But in reality, this has a little bit more messy. So
the full picture also has this interesting effect, what we call one halo term, and that is basically talking about if you have several galaxies within the same halo, then they will not experience this infall, but they will have what we call random motion because of the virialization of the things, and that's what appears as this extension along the line of sight. So this is also known as finger of God effect or one halo term. And this is for the first time we try to extract this to show the full one halo term, subtracting the large scale large scale inward flow, and you can see the nature of this as it extends to not just in terms of the length scale of one halo, but far beyond that. And so this is very hard and messy to model. So one of the implications of this hard and messy to model, as I already mentioned, there is a sigma 8 discrepancy arising. So Planck has a submeasurement, weak lensing has some measurement. Now if I were to look at use these maps I showed you, which is two-point correlation function, to measure the omega matter sigma 8, depending on what I assume about these galaxies, whether they care about the environment or not, whether the tidal environment around these galaxies is important, we can get slightly different picture in this constraint. So it's very important to be robust against this sort of physics. And so the purpose of my talk is I want to talk about, like, can we make this measurement in several ways such that we are robust against these different galaxy type, effect of environment, and all the nonlinear physics. So the answer is galaxy groups. What are galaxy groups? If you look at some of the massive dark matter halo, what you'll find is that there are several galaxies in this living within this dark matter halo, and so we have algorithms to find these things. So imagine in your survey you can go and figure out where are all the dark matter halo, which is same as finding all these galaxy groups. Now you can start thinking about what are the infalls of these around of different kind of galaxies around different kind of groups, and then what if you look at different kind of galaxies for the same infall, what happens? And so that will give you a sort of several different ways to measure the same thing in terms of cosmology, but there will be different astrophysics, there will be different environmental effects, there will be different nonlinearities. And so this is basically main plot here, which I'm going to reveal slowly because it's a secret, but it's not a secret, it's already there in our paper. But what I want you to consider is that basically three main variables. If you think about halo mass, let's say we have this distribution of galaxy group, we can look at different groups of different halo mass. So I did this exercise with three different mass range. So starting from low mass to high mass and medium mass and high mass. And what you see is the nature of this correlation function is very different, because, and that is the major part of the difference you are seeing here is really governed by the properties of the group themselves rather than the cosmology. They should all see the same large scale peculiar flow because they are living in the same universe, they are experiencing the same cosmology. So that's the idea. Now we can also divide the galaxies in different kind of galaxies. So we can look at red galaxies and blue galaxies. So red galaxies are these galaxies which are quenched. They are generally considered to be more nonlinear. They are living in clusters and groups kind of environment. And the blue galaxies are more galaxies which are more young and star forming, and they are generally experiences less nonlinearities as far as galaxy clustering is concerned. And so that gives you again very different nature of this two-point correlation function, but they are experiencing the same cosmology. So what I'm saying is any of these things you take, you should be able to derive the same cosmology, and that's the robustness test. Now I can do this halo mass and red galaxy type split for basically both of them. So red galaxies, blue galaxies, and then different halo mass. And now you can try to model this. There are various prescriptions to model this. I will not go into detail of how we exactly model it, but what we are using is what we call halo streaming model. So we have some recipe to talk about what is the large scale flow, which is essentially more or less linear theory at a one loop perturbation order. And then you can think about how to model the extremely nonlinear scale, and here we are using simulation based approach. So when we combine all of that, we produce these different best fit of our models. So these are models, and you can see the main difference you are seeing between the models versus actual observations in the survey is basically the noise. These are much smoother compared to what is there in the data. And so we need to measure covariance matrices and do a formal statistics to see if our model can describe what we observe. And this will give you basically 6 different ways to measure the same cosmological parameter in different type of galaxies and dark matter halo. So we have done that exercise. There are some, if people are interested in how the theory works, I can talk about more offline, given the interest of time. But based on these things, this is a complicated plot. All of this is about groups and galaxies and what the velocity dispersion of galaxies is in one halo, all that kind of term. The interesting cosmology is essentially summed in just the first panel here. What I'm showing is F sigma 8, where F is in lambda CDM picture, F is omega matter to the power 0.55. And so we provide measurements for basically different kind of galaxy cross collisions. So all the red ones are shown in red color and all the blue galaxies are shown in blue color. Then we also applied two different kind of models. So filled and open points are two different kind of model, which also have appropriate different scale cuts in terms of nonlinear scale. And then we also deal with somewhat there's a fuzzy boundary between red and blue galaxy. I've told you that there's red and blue galaxy, but there's actually a continuum. There is what is called green valley, and so where you draw that cutoff, and there are some details about how do you draw that cutoff. When you allow some variations in that, then those are the purple color showing that. And what is shown in the black point is what you'll predict if you take Planck lambda CDM best fit measurement, and then predict use that to predict F sigma 8 at these for these survey redshifts. And so what is interesting here is that all of these measurements are low, but significance of how low it is compared to Planck prediction is different. But what is even more interesting is that they are robust. So you find that your cosmology is consistent independent of what exact recipe you use in terms of modeling. It's independent of what kind of halo structure you are looking at, independent of what kind of galaxies you are looking at. And so that is the kind of robustness test. I think Shabbir also highlighted that we should do these robustness tests in our cosmological principle, especially now we are seeing this interesting regime. There are many other interesting science you can do once you have these sort of samples of galaxy group, which I am happy to talk about over coffee in more detail. If anyone is interested, you can think about many of the galaxy formation physics. You can look at what are the AGN populations in these things and what are the triggering mechanisms. So there's a lot more things you can do apart from measuring F sigma 8 and cosmology. But that was the main motivation for this work, where we looked at group galaxy cross correlation. And so with that, without going into more detail about the modeling in the interest of time, I'd like to essentially convey that the galaxy groups are a very interesting topic. We should look into it more closely. There's going to be wealth of data set. So right now the examples I showed you is using gamma, which is about 180 square degree. It was done at AAT. We are performing already a survey called DAISY BGS, Bright Galaxy survey, which is going to cover 14,000 square degrees. So that's more than 100 times bigger sample. We are also in the process of doing a survey called 4HS, which is on foremost telescope Vista. That's again going to cover 14,000 square degree in the different part of the sky with some overlap. And so really we are going to, what I've shown you like a few sigma tension, we are going to have more than 200 times bigger data in the next 5-year time scale. So right now is the time to think about this. There's lots of questions in terms of how do you model it, how do you improve your nonlinear prescriptions. So if you are interested in modeling gravitational collapse and things like that, right now is the time to get your theory tools ready and start thinking about these problems. Thank you.
Okay, thank the speaker. It's time for a few questions.
Quick question. I mean, why the blue error bars for blue galaxies systematically much smaller than the red ones?
Yeah, so the reason is that for our modeling, we were able to show that for blue galaxy, we can go to much smaller scale without producing any bias in our model. And the reason for that is that it's less nonlinear in terms of, so our corrections are good enough to smaller scales, and that gives you smaller error bar for blue galaxies.
F sigma 8 is degenerate in linear theory, but since you're pushing to small scales, in principle you can disentangle F in sigma 8.
Yes.
So can you turn the F sigma 8 constraints into constraints on F, which is the growth, and on sigma 8 separately?
Yes.
Like this as a test of GR at the same time as.
Right. So you can do that, but as I mentioned, the nonlinear scales are messy. So we are modeling it in such a way, our F information is more or less coming from the linear and quasi-linear scale. Okay. All the nonlinear scale is used to model all the higher order parameter like higher order bias and what happens to the velocity dispersion, what happens to group bias. When the precision improves, then you will be able to break many of those degeneracy, and then you will be able to disentangle F and sigma, and you'll be able to measure both.
So when you are modeling it, like in a real case, the structure will be almost unstructured. It is like filamentary structures are there. Okay. So and your peculiar velocity will actually depend on how the your halo is structured, right? So how do you take care of that? Because most of the theory that you implement is like spherical collapse models and all. So how?
Right. So that's a good question, and that's precisely one of the point I'm trying to make. If you look at different kind of, let's say, groups of different sizes, the structures are going to be different. And so these are real measurement in case it's not clear. These are real data, and these are our best fit model. What we are looking at, we are not looking at individual objects. We are looking at sort of what we have been mentioned before. We are stacking all the groups. So we are looking at all the groups together, and so we are averaging many of the environmental effect in terms of the large scale environment. So that's one thing which helps. In another way, in terms of modeling the really nonlinear structure, we are not using spherical collapse model. We are in fact using full n-body simulation here on top of adding galaxy physics to that. So what we are still missing is we are missing the details of the hydrodynamics, if there is something is going to affect these galaxies.
At a small scale, it will really impact because like bullet cluster kind of.
So at a small scale, it's going to affect matter distribution more strongly. But what we are looking at is we are looking at galaxy distribution, not the matter distribution. And so if you are to do this exercise in terms of lensing, then you'll have to more worry about many of these things. What we have seen so far is that the position of galaxy itself is not perturbed that much because of these baryonic physics. So the matter distribution itself is. And so that has a very strong effect on lensing, but not so strong effect on clustering. But at some order, when we'll improve the precision by increasing a factor by 200 times, maybe we'll start to see many of these effects. For example, effects of assembly bias, which we haven't included in our model. All those things needs to be added in our 3D model, which is why I say, if you're interested in this sort of, there's a lot to do in terms of theoretical model and developing those models and making them more accurate.
Hi, nice talk. So I have a follow-up question on a similar topic. So which simulations do you use for modeling? Like, do you take into account feedbacks?
No, so these are n-body
only n-body, no baryonic physics.
And then on top of n-body, we have also used galaxy formation models like GALFORM. So these are semi-analytical models, which have some semi-numerical ways to account for the feedback, but it's not like a full hydrodynamic simulation.
So that means these are mostly like painting stars of certain color, depending upon the halo models. Like anti-hearing and...
No, so this is not halo model. So we do use halo model, but we also use GALFORM, which is not quite halo model, but it actually looks at the full merger history of the halo and predict what should be the luminosity in different bands, and then that gives you color of the galaxy.
Because what I'm trying to understand is what is the next level of uncertainty in your measurements, so which can actually kick in because of you don't understand simulation very well so far.
Right. So that is something we have looked in, and that's what I was trying to. So that was basically Arka's question before also. In principle, we can already constrain sigma 8 and f both if we try to. We have modeled it in such a way that our cosmological information is only coming from this 2 halo term what I showed, and so everything else is the smaller scale is still useful because it allows you to constrain all the galaxy effects more better and break some of the degeneracies.
Thanks.
Okay, let's thank Shadab again. So our next speaker is Shabbir Shaikh.
Hello everyone. I'll be talking about CMB weak lensing and galaxy weak lensing cross correlation. We have heard throughout this meeting all the praises about how cross correlations are promising, and here I will talk about one particular example where we take CMB weak lensing map from Atacama Cosmology Telescope data release 4 and galaxy weak lensing catalog from dark energy survey year 3 dataset. So this is the work being carried out with this set of people as a joint effort between ACT and DES collaboration. So this is in preparation work. So all the plots I will be showing are either based on blinded data set or on simulation. So we all know that the radiation from the cosmic sources such as CMB and the galaxies in between is deflected by the large scale structure between the sources and the observer. Now these deflections for most cases are quite small. For example, in case of CMB, it is of the order of arc minute and falls in the regime of what we call weak gravitational lensing. Now, some knowledge about this deflection field allows us to reconstruct a measure of this projected mass distribution, and that is important. So, we get a map of mass from such observations. The effect of this lensing are quite small and mostly appear on the very small scales for the CMB. So here is a lens CMB map. The difference between this lens map and its unlensed counterpart, which is exaggerated 5 times, is shown here. So you can see very small scale fluctuations. The lens that is responsible for this deflection is shown here along with the deflection field. Now the thing to note here is that we have the small scale fluctuations being caused by these lenses which are at relatively large scales. So in harmonic, so the way people reconstruct these lenses is to look at the off-diagonal terms in the Fourier modes of these field coefficients. So these off-diagonal terms are like the contribution of lensing to this off-diagonal term is given by a simple first order expression where kappa is called convergence and it is a weighted line of sight integral of this matter density contrast. So we have these large scale lenses being reconstructed from the small scale fluctuations. Also in the case of galaxies, the effect of the lensing is to induce or change the ellipticities of the galaxies in a coherent manner. Now the galaxies are not all spherical, so that intrinsic shape of the galaxies acts as a noise. However, so in that case, the average value of the ellipticity over a local patch of the galaxies acts as a measure of this shear. Now the shear and the convergence that I just described are related. For example, E mode of this spin-2 field shear is related to convergence through a simple relation. So the shear also gives us a probe of matter distribution. So this convergence is a weighted integral of matter density, and this weight depends on the source redshift. So for CMB, for example, which is at redshift of 1100, this weight is quite broad and peaks around redshift of 2. For galaxies, for example, which are located, let's say, between redshift of 5 to 1, so 0.5 to 1, this black curve shows the lensing weight. Now the thing to note here is that when we take the cross correlation, the product of these two weights probes a slightly different redshift coverage. Now you can see that this cross correlation probes a slightly different effective redshift range, which is not accessible to the galaxy survey on its own. So in case of this particular cross correlation, one of the summary statistics that people look at is angular power spectrum between these two fields, which depends on the product of these two weights. So in case of DES source galaxies, which are in 4 different redshift bins, this is the weight of the cross correlation for this particular cross correlation, which probes sort of redshift 0.1 to like 0.9, and through its dependence on the matter power spectrum, this particular statistics is sensitive to what we call sigma 8 or the SF parameter, which is combination of omega m and sigma 8. Now it so happens that the value predicted by the based on the CMB observations for this parameter, and what is observed at lower redshifts is discrepant at around 2 sigma. And this particular probe is a promising measurement which can shed light on this as it probes a slightly different redshift range. So it is slightly different measurement of the sigma 8. Now this particular measurement has become more and more precise over the last 10 years. So for this our particular work, where we use ACDR4 lensing map over this D56 region, overlaps with this year 3 map with 500, like around 450 square degree of common sky patch, and the SNR we expect is around 9. For the upcoming ACT data release, which is ACT DR6, expected this year, the overlap area is going to be around almost all of the day's footprint, which is around 4,000 effective square degrees, and there the precision is going to be around 4%, and that would be a very interesting measurement to look at. So what we cross-correlate effectively is a mass map that is based on a CMB, which is same region as this for the ACT footprint, and the ACT provides, for example, this is a mass map, which is the convergence. However, for this particular measurement, we use the actual shear map instead of the kappa map obtained from the shear map. Yeah, so this is a typical pipeline that the analysis goes through. So we generate the theory. So to obtain the covariance matrix, we use simulations, and the simulations are of the log normal signal maps of this kappa and shear, with the realistic noise for this particular observables. We use certain scale cuts to avoid certain biases. At low L, to avoid the mean field bias coming from the mask of the CMB maps, we use L mean of 100, and to be less affected by the baryonic effects, we put L max of 1900. And so here is a comparison, for example, of the input theory and the mean of the band powers for this cross obtained from simulations. Now ACT provides two kinds of CMB weak lensing maps. One uses ACT only CMB maps. Another uses ACT plus Planck dataset, where thermal Sunyaev-Zeldovich contamination that exists in the ACT CMB maps is deprojected. Now it is important to remove this TSG because TSG also traces the last scale structure, and the shear map that we are talking about also traces the last scale structure. So generally we say that the cross correlations are immune to systematics. However, if there is a contamination in any particular probe, which we are unaware of, and that spuriously correlates with another probe, then of course you are not going, you are not being immune to that systematic, and such things need to be taken care of. One more plus point over here using the Planck map is that we get an additional signal. Generally, TSG projection leads to increase in the noise. However, there is additional data set, hence we don't incur much noise cost. So we blind our desk catalog to be blind to certain choices. So these are the blind data vectors, which could be as good as the simulation data vectors. So we do some certain null tests to make sure that there are certain non-idealities not present in our data. So this is a B mode null test, which looks for the spurious B modes in E to B mode, like when we obtain a E mode map from the shear map, and this is a rotational test. So in both the cases, we expect this signal to be like this data set to be consistent with 0, and that is what we find. And so we can do a cosmological analysis. Now these are the results based on simulations for the sigma 8 and omega m or S8 and omega m parameters. So we expect to get a constraint on S8 of 0.06 from this measurement, which is not very competitive at the moment, but with ACT DR6, it would be around 0.03 which is going to be competitive with other probes. So this constraint is actually obtained by marginalizing over certain systematic parameters. So those include photometric redshift bias and the multiplicative shear bias. However, for this particular data set, we are not at all sensitive to these particular nuisance parameters, as you can see that the constraints are as good as the prior that we put in. However, it is important to marginalize over these kind of nuisance parameters so that our constraints are not biased. So I will leave you with the summary. Thank you.
Thank you, Mr. Speaker. Now it's time few questions.
Two questions. So how does the error bar on S8 in this analysis compare with the SPT analysis?
Yeah, so SPT analysis only using the cross between CMB and Galaxy, and the CMB and the Galaxy lensing is around 0.03.
Okay, and that's because they're deeper or more sky coverage,
It's
which is
a combination of both.
And then
the ACT noise on that D56 region, like that's just 400 square degrees, is quite good, but had it been wide, then it would have more.
One of the other things that, considering galaxy lensing, cosmic shear and CMB lensing together was supposed to do was get rid of the need for having a multiplicative bias parameter. You could self-calibrate. Do you think you'll get there in the next data run, or it will be CMB stage 4?
It would be like, one would actually have to run a chain to see that. It's difficult to see the trade-off between various parameters. Then there is intrinsic alignment, which I have not shown.
Yeah, thanks.
So I want to ask, what about the contaminations from the CIB at this level?
Yeah, the same thing exists. Like this TSZ bias that I mentioned, so you can have bias from CIB too.
Did you see how much it is?
At this, for this SNR, it is not that. It seems to be like from the other studies, it doesn't seem to be that important at the moment. But with more and more high precise measurements, one has to worry about that.
And how do you include the foregrounds in this? Did you include any foregrounds in your simulations, or you
no, we didn't include any. Yeah. So for simulations, it's mainly the noise that we assume for whatever this setup.
If no, thanks Sabir.
Thank you.
Thanks Sabir again. Now we have lighting talks, and we have 6 lighting talks.
Hello everyone, I am Kumar. I'm a PhD student at IIT Indore. First of all, I would like to thank the organizer for giving me the opportunity to present our work. Today I will present my poster titled "The Effect of Earth Ionosphere on Your Observation with Radio Interferometer." The most sensitive operational interferometer like GMRT, LOFAR, MWA, and HERA have all set the upper limit on power spectrum amplitude on 21 centimeter signal, but no confirmed detection of the signal. So these observations are made challenging due to the astrophysical foreground like galactic synchrotron emission, extragalactic periphery emission, Earth ionosphere, radio frequency interference, and in instrumental systematic. The highly sensitive next generation telescope like square kilometer array SK1 low make the tomographic images of the signal. So to understand each of these corruption terms, we have to set up and pipeline to deal with the synthetic observation at the low frequency. The Earth ionosphere introduced the phase corruption to the extragalactic signal at less than 1 gigahertz, and they cause the directional breaks, means that they vary across different directions, and that causes the apparent position shift from the original position from their actual position. So this is the schematic pipeline. Look here, and we first simulate the true sky, which is free from any error, and add the ionospheric term and see how this error will affect the accurately measure the power spectrum and see how the error will affect the 21 centimeter signal extraction. And we first simulate our true sky, and the sky model consists of redshifted 21 centimeter signal, which is generated from 21 centimeter first, and we use T-rect point source model as a foreground, and we take array configuration having 2 kilometer baseline is shown in here, and we run our simulation, and we and to incorporate the ionospheric effect, we simulate aerodynamic sky model using various positional offset. And if you want to know more details, so please visit our poster. And we subtract the true visibility, which is mentioned in the model visibility, and from the Coda visibility and make the residual visibility. So as you look in the panel, which is basically the point source is dominant that I put in. So I first make the plot, which is the RMS versus the apparent position offset, and here is shown here the apparent position offset is 0.01 arcsecond, which is below the signal level. That means we can detect the signal, which is just the 21 centimeter signal. And next, what we have done, that the cylindrical power spectrum, which is the signal power spectrum, and we increase the ionospheric coefficient, and see here in the left to right the residual foreground start leakage to the UR window, and if we and then we find out our spherical average power spectrum, and the red line which is shown here the signal power spectrum observed by the SQ1 low, and the 2 arcsecond position shift of the residual foreground, which is mentioned in the blue line, which is essentially below the signal power spectrum. That means that we can detect the signal accurately. So that's it.
Thanks, Samir.
Thank you.
Next, Anjan.
So thanks for giving the opportunity. So I would like to present the work which I have done about a year before with Shiv and Kanaya, and I will very briefly discuss what we have done. What we have done is called the redshift evaluation of the Lyman alpha opacity, and use it as a probe of the dark matter models. That means to say alternative dark matter models. So to begin with, this is the Lyman alpha forest, and this forest-like structure bluebird of this Lyman alpha spectra, Lyman alpha peak, is called the Lyman alpha forest. And this is primarily arising from the density fluctuation, which is of the order of 10 to the power minus 4 in the mean neutral hydrogen fraction. This is believed to be a very powerful probe of the small scales of the IGN at very small scales. Now, to give a bit more detail about what Lyman alpha forest is, this corresponds to a mildly nonlinear fluctuations in the IGN, roughly of the order of delta of the less than of the order of 10, and these are large diffuse structures having temperature of T of the order of 10 to the power 4 Kelvin. These are quite large in size, 0.1 to 1 megaparsec, and in comparison with galaxy surveys and CMB observation, this can probe up to 5 megaparsec inverse, where the galaxy surveys and CMB can only go up to 0.2 and 0.3 megaparsec inverse respectively. So all in all, this is a very powerful probe of the small scale. So there are certain problems which exist with the existing CDM model. This is called the small scale crisis. One of them is called the missing satellite problem. CDM simulation always predict more satellite than is observed in the local groups. And also there is a core cast problem. That means it produces satellite galaxies which has the core density profile shows a cusp. Now, to mitigate all those problems, a different class of models has been proposed, which are called the alternative dark matter models. We have only considered 2 classes of models. One is called the WDM model, or the warm dark matter models, and ULA model, ultralight axion model. Although the origin of the in both the models, what is common is that in both the models at the small scales, the matter power is suppressed in comparison to what was there at the CDM model. Now, origin of the suppression in both the models are different, but what is common in both the cases that there was suppression at small scales, and at sufficiently late times, both these models behave as the CDM model. Now, question is, this is all of the problem of the small scales, and we have a very powerful probe of the small scale called Lyman alpha forest. So, whether we can use it to probe the WDM model or ULA model, or distinguish the WDM and ULA model in comparison with reference to the CDM model. So, We have gone on to simulating the Lyman alpha optical depth, because this Lyman alpha optical depth is the observer that we have for Lyman alpha observations. So for that we followed some steps. We start with the power spectrum, scatter power spectrum, and then we simulate the baryon number density. Then using a set of parameters called the nuisance parameter for the Lyman alpha clouds, we simulate the H1 number density. And then we calculate the optical depth along a given line of sight. And then we simulate the same thing for different line of sight, take an average, and following this formula, we can get the effective optical depth at a given Z. So following this relation or this procedure, we can simulate the effective optical depth at a range of redshift. Now to compare with, we need some data. So, So compare with the data, we have used something, the observation was taken by Foshak in 2008. It's a high resolution observation of quasar spectra, and it covers the Lyman alpha forest optical depth over this range 2 to 4.2. We have used for our purpose only this delta V, which lies in the ballpark of the velocity resolution used in the instrument which was used to take the data. Now, to compare, so we have this tau effective from data, and we have also simulated the tau effective or effective Lyman alpha opacity using simulations, and then we want to compare. To compare, we have chosen this set of parameters, which are the nuisance parameter for the Lyman alpha clouds, as well as the mass, which alone determines the character and the shape of the alternative dark matter models in comparison with the CDM model. So now we go to the result. The result basically shows that after marginalizing over all the other parameters, because mass is the only parameter which alone determines the shape and the character of the alternative dark matter models, we see that it is always consistent with the highest mass that we have chosen. So basically this indicates that our analysis indicates that both the alternative dark matter models are consistent with or compatible with the CDM model prescription. Because as you may have been aware of, that for the mass goes to infinity or for the very large mass, these all models actually boils down to reduces to the CDM model. And if we talk about the scale, this is sensitive to scales up to 2h megaparsec, which is quite a nonlinear scale. Now, this is the key outcome which I already mentioned, that our analysis shows that even the alternative dark matter models scenario, that the Lyman alpha data are consistent with the prescription of a CDM model for the universe. So this I will stop there.
Thanks, Ranjan. Next is Anoma Ganguly.
Hi everyone, I am Anoma, and this is a recent work that I did with Rishi Khatri and Tuhin Roy at TIFR. Okay, so according to the standard model of cosmology, about 75% of the matter content in our universe is dark matter, about which apart from gravitational interaction we don't know anything. So in this work we propose a new signature of dark matter that could arise as absorption lines in spectrum of a background source. So think of dark matter as having two states where the transitions can happen via photon or via collisions. So in the first case, we consider CMB as our background source, and we find that if dark matter can have collisional and radiative transitions, then this kind of dark matter can give rise to an absorption signature, which can explain the edges anomalous signal. This is similar to what you have for the 21 centimeter signal during the dark ages. The only difference being the high redshift part of the signal, which is decided by Bremsstrahlung, which is important before recombination and at low frequencies. And note that here the absorption is actually coming due to dark matter, and this is not due to hydrogen. Okay. Now, if instead of CMB you have quasar as your background source, which is compact source, then along the line of sight to the quasar, you will have many dark matter halos, and each of these dark matter halo is going to absorb some photon, and due to expansion of the universe, this is going to give you a set of absorption lines, something similar to what you have for hydrogen, like Lyman alpha or 21 centimeter forest. Now what you can do with this forest is, this is a collection of lines where each line has an amplitude and a width. So we can then count how many lines correspond to a particular amplitude. So this is what we do here, and what is the key takeaway is that this kind of 1D PDF can distinguish between the collisional nature and collisionless nature of dark matter. Also, the halos that you're intersecting, that is sensitive to the halo mass function. So that is sensitive to the minimum halo mass for dark matter. Same thing one can do for line width, and here again we find that these line width distribution function is sensitive to the halo mass function. And what kind of dark matter can give rise to this kind of signal is basically a bound state, which is made of two particles having equal and opposite charges. These charges have to be small, so that the photon can make transition, and these are not like atoms. But dark matter has to be stable, so the stability comes from strong interactions of the dark sector. So you can have dark matter somewhere here, which can have a splitting. And there is no reason to believe that there will be a particular frequency. It could be in the whole electromagnetic spectrum, and it could even fall in the Apsara band. So just to summarize, like we propose new signature for dark matter as absorption lines, which can arise as a global feature or spectral distortion in CMB, and it can give rise to dark forest in the spectrum of wave.
Thanks, Anoma. Next speaker is Rajoshi.
Hi, I'm Rajoshi, and I'll basically give an overview of the weak lensing challenges in cosmology, in CMB cosmology, and how it connects information from inflation, from the era of inflation all the way to current observations, like at the current time. So why do we study CMB weak lensing? So lensing is a very versatile carrier of information about the fundamentals of cosmology. So it acts as both as a contamination as well as a source of information in itself. So you can think of it as if you're watching light through a window and the window itself has some defects, which both the defects as well as the light coming through the window are sourced from the same primordial fluctuations. So that's how you can see lensing as both a carrier of information as well as a contamination. So in the information side, you have the lensing power spectrum, the weak lensing potential power spectrum CL55, as well as the map, and they carry fundamental cosmological parameter information as well as can help constrain data from other sectors such as cross correlation with galaxy surveys, etc. As well as lensing needs to be cleaned from, let's say, the B mode polarization CMB signal because it's a dominant contamination. If you have a primordial signal, you need to understand lensing well and characterize it to be able to clean it from the B mode. So a brief cartoon on lensing. So these are the CMB photons from the surface of last scattering, and as they travel throughout the matter distribution of the universe over all redshifts, and when we see them finally today, they appear lensed. And this is a simulated map of how the lensing actually affects the CMB observation modes. So the unlensed T, E, and B mode anisotropies, and this is after lensing. So you can see the B gets contaminated with lensing as well as the changes in the T and E modes that lensing causes. So these are forecasts from next generation experiments that would in which better constrained lensing with smaller error bars would help determine fundamental cosmological parameters and for cleaning the B modes. So this is the neutrino mass sum, and these are the error bars of CMB S4, and these are the different models for the neutrino mass sum that can be constrained with better error bars on the lensing power spectra. And this is the B mode where the yellow line is the lensing contamination. And for different tensor to scalar ratio, your primordial signal could be below it and would require cleaning. So so essentially it's a convolution. Lensing and the unlensed temperature anisotropy fields, we can model them to be Gaussian and statistically isotropic, and the two get convolved, and what you observed is a lensed temperature anisotropy map and the power spectra, as well as the lensing potential map and power spectra that you can reconstruct from the temperature anisotropy and the other modes as well. So in the first section, what we do is we apply the Richardson-Lucy deconvolution algorithm to the lensing potential power spectrum, the CL55, and assuming the lambda CDM model for the evolution kernel, we try to reconstruct the primordial power spectrum, the scalar primordial power spectrum, the seed fluctuations from the observed lensing potential power spectrum. So this is an iterative estimator where this is the data you put in, and this is the initial guess for the iterator that you use, and you iterate it until you get a converged estimate for the P of K. So the details of how this estimator can be derived, I can tell you at the poster. So these are the results for this kind of simulated data, which is the lensing potential power spectrum with cosmic variance limited error bars, this is the kind of reconstruction you can expect. The orange is the injected power law model for the primordial power spectrum, and the blue one is the reconstruction with full error bars and covariance, full covariance matrix analysis for validating if you find some features in the primordial power spectrum. The other project that looked at lensing was to see how to de-lens the temperature power spectrum when reconstructing the primordial power spectrum from it. So what happens is, this is how the lensed power spectrum for the temperature anisotropy behaves under the effect of lensing. These two terms are added, and as you can see, this now makes the kernel non-linear in the sense that it itself becomes a function of the P of k, where originally it was not. So how do you account for this? We basically introduce an iterative corrector in the previous Richardson-Lucy estimator, and we show that if you apply it on lens temperature power spectra, this is the kind of cleaning you can get. So this is the ideal reconstruction, where this is some test feature we're trying to reconstruct from the primordial power spectra. This is when you ignore lensing entirely. This is when you use a power law template method used in previous literature, and this is our method where we use the iterative model-independent iterative correction method. And the third thing that I want to talk about is reconstructing the lensing map and the power spectrum itself from the temperature anisotropy data. There's a very brief overview of the minimum variance quadratic estimator, where this is your estimator for the lensing map. This is the reconstruction noise or the variance of the estimator, and you minimize it by the method of Lagrange's method of undetermined multipliers subject to the constraints for these weights. These are when you average over your observed temperature map modes. And what you essentially get is this kind of reconstruction where you have the red is the injected input, and after correcting for several biases, you get this cyan reconstruction. As you can see, there is some mismatch here. So these are open areas of challenges where you have higher order covariance terms, which are usually neglected for current generation estimators, but we are looking at on how to incorporate them at the map level estimator for this minimum variance quadratic estimator. And there are some interesting results that we have, and we expect to validate them numerically soon. So these are the conclusions, that the Richardson-Lucy and the sparsity sampling method is a really good window for getting the lensing map and the power spectra, and the non-linear iterative correction method is also equally efficient. So please drop by the poster.
Thanks, Rajesh. Our next speaker, Akash.
So today I'll be talking about searching for primordial black hole dark matter with global 21 troughs, and this is based on a work done in collaboration with Ranjan Laha. So as you all know by now that around 85% of the matter content in the universe is made out of dark matter, but besides its gravitational nature, we know very little about it. And there are many different kinds of dark matter candidates, and the one that we are focusing on here is primordial black hole. So the first question is, what is a primordial black hole? Well, primordial black hole is just like any other black hole, but these are formed at a very early stage of the universe. And after formation, if we know the mass and the spin parameter, we can determine the temperature, and depending on the temperature, these primordial black holes will Hawking evaporate. And what that means is that they will produce a bunch of sternal particles. And the spectra for that is given here, where this gamma is something called a gray body factor, and this E dash is the total energy of the emitted particles, taking into account the black hole's rotational velocity. So the next question is, how to detect these low mass primordial black holes? Well, as I said earlier, that these primordial black holes are Hawking evaporating. So what that means is that they are injecting a bunch of particles in the surrounding. And what that will do is that it will alter the thermal and ionization history of the intergalactic medium. So if I have a sort of thermometer that traces the thermal temperature of the IGM over all the redshifts, then I can say whether or not it's possible to have primordial black holes. Now, luckily for us, we have a thermometer, and the name of the thermometer is global 21 signal. So what is the idea? So here in the x-axis, we have the redshift. In the y-axis, we have the differential brightness temperature, the thing that we measured in global signal. And let's say this blue line is something that I expect from my Landau-Sedum cosmology. So this is from theory. Now let's say I build my own experiment and try to see the signal, and let's say this red line is something that I detect. So what this tells me is that there is a possibility that in this redshift range, there is exotic heat injection. And one candidate that can give me this exotic heat injection is primordial black hole. So in future, if we find any excess in these global 21 troughs, then it's possible to search for these low mass primordial black holes. And even if we don't find any excess, that is also interesting, because that will help us to constrain large regions of parameter space. And that is exactly what we do.
So in the x-axis we have the mass of the primordial black hole in gram. In the y-axis we have FPBH, and this FPBH parameter tells you the fraction of dark matter made up of primordial black hole. So if I say FPBH is 1, then all dark matter is primordial black hole. Now this left panel is for non-spinning primordial black hole, this right panel is for the spinning primordial black hole, and the shaded regions are ruled out by various kinds of astrophysical observables. So if you are interested, I can talk more about it afterwards. So here what you have done is that we have taken 3 different values of global 21 centimeter signal at redshift 18, and these are all allowed by lambda serum cosmology. And using these are the bounds that we obtain. So for example, let's take this purple line T21 equal to minus 200 MK. Then what that means is that anything above this purple line is ruled out. So as you can clearly see, even with considering the standard global 21 centimeter signal, we can probe new regions of the parameter space that were not ruled out. Well, the next question is where do you start to look next? And as many people have already discussed, that we can try to look at the dark energy stuff. And the reason why this is very important for fundamental physics is for the reason that we know for a fact that this stuff is free from any kind of astrophysical contributions. And what that means is that, let's say in future we have a measurement and we have an excess, then there is no way that you can explain that excess using astrophysics. There has to be new physics. And that is the reason why this stuff is very important. And as many have already said, that there are some proposed experiments that will try to go to the far side of the moon and try to look at this high redshift stuff. So in our work, what we did is that we took the standard lambda CDM cosmological expectation of this dark energy stuff and again used to bound the property of primordial black hole dark matter. So the same plot, in the x-axis are the mass, in the y-axis are the FPBH, and the green and the red lines are the bound that we obtain. Again, the shaded regions are all ruled out. So as you can see, these are sort of competitive with the other existing limits. But the important fact here is that in order to probe exotic physics that injects heat in the surrounding, you have to go to the dark energy stuff. So to conclude, we have seen that global 21 centimeter signal can act as a calorimeter. Low mass primordial black holes can Hawking evaporate and affect the temperature around it. And we hope in future we will have many such global 21 centimeter signal measurements, and that will help us understand the evolution of the universe and also the nature of dark matter. So thank you.
Thanks, Akash. Next speaker, Shumon.
Thanks to the organizers for this opportunity. So today I am going to discuss about this tracking tapered gridded estimator, which basically concerns regarding drift scan observations. So the primary difference between a drift scan and tracking observation is that when in a tracking observation you look at a particular patch in the sky with your telescope and you track it, whereas in a drift scan observation you point your telescope towards zenith or something and then you let the sky drift in time. So there are few advantages for this drift scan observation. One, primarily the stability of the instrument, and it has been shown that it can provide a better SNR for a 21 centimeter observation. So as we have seen earlier, that these wide field drift scan observations can be contaminated by the foregrounds that cannot be modeled which are far away from the primary beam, and Nicole has earlier shown beautifully that how a side lobe contamination can affect your measurements. So here, as Somnath also suggested, that here we propose a technique which basically tapers out the side lobe contaminations in the process. So this basic formalism is something like this. There are two nomenclatures, one is pointing center, one is tracking center. So basically these denotes the pointing center where your telescope points and basically drifts, and there is a tracking center which you track with time and that doesn't change. So you taper, okay, so if you take a cross section it should look something like this. So you have your primary beam which is this large envelope, and you taper it with a function which if you have which will be smaller, which is shown in this black line, and if you have a large enough beam you can move this tapering window within the beam to access different regions of the beam. So there are two basic strategies that we focus upon. One is that there are no contaminations within the beam that you cannot model out, only the side lobes are the troublesome feature, and you use the whole beam with a large size tapering windows, and you estimate your power spectrum. Sorry, whereas you may have a contamination within the beam which you cannot model out, then you can try putting small tapering windows within the beam according to your choice and weigh down the observation accordingly. So we have shown that a coherent addition from different pointing center and incoherent addition from the different tracking center can lead to a SNR improvement in of significant number. And we have also shown that this particular estimator successfully suppresses the point sources which are in the far away from the main pointing center of the telescope, which is shown here. So a simple, comparing with the simple estimator, we showed that this particular estimator can suppress a significant amount even if the point sources are at the horizon. Okay, so the second point I would like to address is some systematics that is particularly dedicated to MWA-like observation, which is the periodic missing channel, and we have used the MAPS estimator to estimate the cover spectrum for our case, and we have shown that this estimator works beautifully. And even if with these flag channels and the data, we are able to recover this 21 centimeter signal successfully. So there are few takeaway points are like this, that we have developed a new estimator which is tracking tapered period estimator, which is suitable for drift scan observation. It can suppresses the point sources or other foreground contamination which are in the side lobe regions. So this particular TTG works with the gridded visibilities, and so it is faster, and it also corrects for noise bias internally. So coherent addition helps us to reduce the noise, and incoherent addition of different tracking center helps us to reduce the cosmic variance. So we have also addressed the missing channels in MWA and mitigated with tracking this particular estimate. I'll just make it.
Thanks, Shumon. And also thanks all the speakers in this session.